will be cluster. I will put those structures, meaning that could be cluster varieties or cluster algebras, both. And on the other side of this arrow will be some representation theory. But this word correlation means it will be representation theory of some infinite-dimensional algebras, like infinite-dimensional algebras. The first approximation one can think about vertex algebras, like W algebras or affine the algebras, but since cluster structures are in some sense multiplicative, so practically here will be Q-deformed. We will live in Q-deformed setting. So instead of standard W algebra will be like QTW algebras. The affine algebras will be replaced by affine quantum groups, and more elaborate stuff like toroidal algebras also appear here. So as I said, the goal to establish connection. This is in progress, so I will state some theorems, and I believe all theorems which I state now have recent proof, but please take care. My goal is to present some idea at least, but the idea which is, at least I believe, is new is really concerns the part which is generalization when we come to the infinite-dimensional algebras. And actually connection between cluster structures and fine-dimensional quantum group is somehow established now, and I start with established. Let me first recall a bit, at least partially, what are the cluster structure, what is a quantum cluster algebras. The cluster algebra starts with an oriented graph. And for beginning, I consider an oriented graph which with two vertices and one arrow. And then for each vertex, we assign a variable, say A and B. And arrows encode commutation relation between these variables. So if we have one arrow, then relation is AB is equal to Q squared BA. And more generally, if we have a huge graph, then commutation relation between variables, say xi and xj, will be Q in power 2 Bij xj xi, whereas this Bij is number of arrows from I to j minus number of arrows from j to I. So this is allowed? It's allowed, but it doesn't affect commutation relations. So you can cancel cycles of length 2 before we come to correlation. In correlation, that would mean something. So practically, algebra which we defined now is just sometimes called quantum torus. So this algebra of polynomials in some variables x1, it's usually considered polynomials considered to be Laurent polynomials, subject of such Q commutation relation. Sometimes it's called quantum torus. Of course, these algebras are very simple, and first connection with algebras-like quantum group is that we can make representations of the quantum groups using these quite simple algebras. The simplest example is the following. Consider the following quiver. Maybe I draw arrows using some colors. So there's a quiver with 4 vertices and actually 4 arrows. And we can define the following expressions. E is equal to x1 plus, okay, let me write x1 plus then these generators, E, F, K, and K prime, they satisfy quantum group relations. To be more precise, here they satisfy relations of the Drinfeld double of the Borel subalgebra. But if you impose that K times K prime is equal to 1, if you take the corresponding quotient, okay, you should make product in some order. Then you get standard UQ SL2 algebra. Of course, you can think that these formulas are quite random. I tried to represent something by colors. So when I define E generators, I somehow go along blue lines. So if I go with colors more seriously, then this E and K correspond to blue part of this graph, and K prime and F correspond to red part. So K is just a product of variables along this line. And E is some telescoping sum, it's first, plus the product of first and second, and it's just a stop. And similar for F's. Since this is partially school, I'm trying to be elementary at the very beginning. Oh, thank you. Organizers applied me the clock. So one way to think about this is the following. So this algebra of Q commuting generators is one can think about this as an algebra of Q difference operators. So these formulas, so equivalently, this is a representation of, if you want, UQSL2 via Q difference operators. So one can take, say, X and difference operator D, which is Q in power X dx. Then this operator Q commute. And then one can realize, take representation of this quantum torus x1, x2, x3, and x4 in terms of X and difference operator. So like x1 goes to X, x2 goes to maybe the inverse. I don't know, so this is a formula at least which is written in my notes, but something like this. And Then you get representation of whole QSL2. Maybe
that over here, x3 is x or lambda.
yes, exactly. So here you have additional variable lambda. So here we have 4 variables. I assume that some product of them is equal to 1, so essentially 3, and they are represented in terms of x and dx, and one additional central element lambda, which is correspond, of course, to the Casimir of QSL2. So we have x, dx, and lambda, which is central. Other questions? Maybe, again, as an analogy, so this realization of quantum group in terms of Q-difference operator should be viewed as a Q-deformation of realization of just Lie algebra in terms of differential operators. So we have action of SL2, we have embedding of SL2 into differential operator on the line, given by formulas like E goes to dx, H goes to minus 2x dx plus lambda, and F goes to minus x squared dx plus lambda x. And then we promote them to Q-difference operators, and then we somehow denote certain product of the operators multiplication and Q shift, and call them cluster variables. Up to now, I defined the things which correspond to one quantum torus, or more geometric torus cluster variety, to one chart. But perhaps the most interesting, most important definition in this definition of cluster variety is the definition of mutation, the operation of glue in different charts. So this is I'm going to define next. I'm not going to give full definition, but I do illustrative example. So assume that we have a piece in the quiver which looks like this. So we have 3 vertices, and we have arrow from A to B and B to C. Then we can do mutation in the middle vertex B. So mutation is, first of all, transformation of the combinatorial data, transformation of the quiver. So we get a new quiver in which all arrows adjacent to B will reverse orientation. And then we should close the triangle, draw arrow here. And this is also supplied with a transformation of the variables. A tilde, B tilde, C tilde. And these new tilde variables are given by the formulas. B tilde is just B inverse. C tilde is C1 plus QB inverse. And A tilde is A1 plus QB. So I'm not going to check this, of course, on the board, but here I already made statements could be wrong. So I stated that if you define U, A tilde, B tilde, C tilde by these formulas, they would satisfy a Q commutation relation which follows from this quiver. And I hope I didn't make a mistake, but this, the good property of this, of the formulas for E, F, and K, K prime, which are there, is the following. So the property the generators of of UQ SL2. Maybe quantum group. Remain are Laurent polynomials after mutation. This is not obvious. So before I said that for any chart we have the Q torus, like Laurent polynomials, and these x variables. When we multiply, we have some Q power. But due to this inverse, this is not. We have no map between. If we have some function Laurent polynomial for one quiver, then after mutation can become not Laurent polynomial. But formals suggest this property holds. And I don't know, I stated for one mutation, but actually for any sequence of mutations, they remain null. Of course, I mean, to make the statement very precise, I need to say more true that actually these two vertices are assumed to be frozen, so it is not allowed to mutate in them, but it's allowed to mutate in these two. What is the rule for these formulas? There are different answers. So first answer is the following. So if I have any other vertex which connects with this B with an arrow, I should multiply by like this. And if I have in opposite way, I should multiply like this. So if you don't have double arrows, this is already the definition. And for double arrow, you multiply something like a square of this, but for square, of course, you should shift argument back differently. For other quantum groups, we have to write larger quivers. For example, if you want SL3, there are two quivers, but okay, I want to draw them, but it would take a bit more time and space. So the number of vertices in quiver, they geometrically would correspond to dimension of the corresponding manifold. So here we realize quantum group like differential operators on P1, and we also have some Casimir. So actually, the dimension of the quantum group SL3 is 3. Or double is 4, and then the number of vertices will grow quadratically. So here we more naturally realize Dirichlet double, so it will go like n squared plus n. I don't know. Okay. No, I'm going to make more comments. I don't know in which order. So when I start to, there is another way to think about this formula that maybe represented using another color. So these formulas, they can be viewed as a conjugation by quantum the logarithm phi of b is just 1 plus qb, 1 plus q cube b. Maybe it's readable. Product 1 plus q in power 2j plus 1 b. So the most essential part, this non-monomial part, transformation is given by this conjugation. And this also applies to some simple monomial transformation. Okay? Any other questions? Sorry? One of the definitions is the following: that the algebra of Laurent element of Laurent polynomials, which remain Laurent polynomials after any sequence of mutations. I am avoiding some technicalities, for example, difference between I don't know, a variables and x variables. And ask me later. Speed. So more geometric, one can think about this as the algebra of global functions, or of this quantization of algebra of global functions. And here it means that it corresponds to the fact that we represent, actually here, we represent SL2 as differential operators on A1, but actually they're differential operators on P1. So there is some additional constraint. We have another chart, like in second lecture today. And this is both additional constraint on functions which we can write, differential operators which we can write. And we actually land to the differential operator which lives on the whole P1.
So the point is that we can say two manifold and we cover it with Toy chart, and these cluster maps are transitions to this chart, then we quantize.
Yes, yes. Yes, a question? What? Yeah, so CTIL is not Laurent polynomial, but combinations which we wrote above for EF, they remain Laurent. This practically is the reason why we take these combinations. Actually, I was told to repeat questions from the audience because people on Zoom, they don't hear. Please remind me to repeat it, or at least summarize. Other questions? I don't know, perhaps you can ask what's the logic of this queer, who told me this, and I'm not, so this queer comes from some geometry of local systems on the surfaces for Goncharov's story, and secretly this quiver corresponds to the disk with puncture and 2 mark points on the boundary. And this puncture secretly lives here in the center. Of course, this is just one chart, or another. So doing mutation, we can come from this chart to others. For example, there is another chart which I like. Another. Chart. It has the following form. this. Maybe yes. Also some horizontal arrows here. And this quiver is now drawn, considered to be drawn on a cylinder. So there's some way to come from this puncture disk to the cylinder. And this way, there is some clever composition of mutations. In this case, just one mutation, but in general, it's a hard question to compare realization in one chart to another chart. But there are combinatorial technique to do this. Okay, let me once again ask, are there any questions? In SL2 case, these two pictures coincide, but actually there is, because you can do mutation, there is one more picture also. In SL2 case also you have freedom. And this would correspond to something non-trivial to formulas of your generator. So here, this realization symmetric, both E and F are sums of two terms. But if you do mutations, then E become one term, and F becomes sum of four terms. So there is some room to play with difficulty of your formulas. Both formulas are, both pictures here are generalized for SLN, and actually there are more nice combinatorial pictures which can be generalized for higher rank. Yes.
To be sure, in this picture, we have this number of columns or one less.
We have 3 full columns and two full columns, and one column is not full. Actually, if you add 2 additional vertices, we will get realization of not SLN but affine SLN in evaluation representation. Okay, hope there's no questions. I'm exactly in the middle of my
Sorry, what was the previous question?
So, question from the Zoom?
What was the question asked?
What was the last question? The last question was, what is the number of columns in this picture, on this picture on the cylinder? So this is a picture on disk, and this is on a cylinder. And the answer is that there are 2 full columns and 1, and 2 is like n minus 1 full columns and 1 is not. Yes, yes. So this, as variables on the boundary, they're usually frozen, and internal ones are unfrozen. Okay, now 31 minutes, so 1 minute more than half, but still, maybe it's a good point to start the talk, and now explain what I'm going to talk about, what is kernelization. Goal is the following. So we have realization of the quantum groups in terms of Lie algebra in terms of differential operator, or quantum groups in terms of difference operators. How about if we want affine Lie algebra or quantum affine algebra? How to realize it? And in this not Q-difference case, such realization goes on the name of Wakimoto realizations. And in Q-difference case, perhaps they're also called Wakimoto. Here considered SL2 or entire paper. There are several papers in the 90s about formulas how to realize about Q-difference Wakimoto realizations. Formulas looks. Some expert told me that they are just horrible and they're a total mess. And Actually, I don't know because I looked on the FSLN, but I think this method works for not chiral world formals exist for any type, and I think this chiralization would work for any type, but I don't know. And if you ask, so perhaps the main idea is you can you can trade these formulas by the pictures like this, by this cluster combinatorics, but with some additional data. So the goal for the next, I don't know, like 10 minutes, give some idea how we're going to explain all these horrible formulas. So we start the same as we started here. We start with the quiver. And again, as a quiver, I consider quiver with two vertices and one arrow. And now the arrows will have some weights. Let me denote this weight by P. And to each vertex I assign, now it's assign a capital letter. And the fact that letter is capital means that now it is not one generator, but rather current of the form like A0 exponent of sum A minus n over n, where this A's satisfies some Heisenberg algebra. And commutation relations between now these generators are given in terms of operator product expansion, as usually in this signs. So we can write A of z b of w is equal to so operator product expansion is here is considered to be bosonic one. So I move all A's with negative indexes to the left and with positive indexes to the right. So here also assumed to be operator product expansion. If you're not very familiar with this technique, so just ignore all the words about operator product expansion. If assuming that I'm trying to represent ideas, they would not affect idea. This is just normal ordering, bosonic normal ordering. Yes. This actually corresponds to singular part. So you have pole but I mean standard theory, the poles are contained on the diagonals like z equal w, and here pole is shifted by this weight of the h. The question of limit is delicate. This is just normal ordering. No. Sorry. Yes. This is just normal ordering. Okay. Actually, there is one more formula. So this is here I defined commutation relations which correspond to arrow, but actually there should be one more formula which correspond to commutation relations which correspond to the vertex. Namely, if I take product of A of z and A of w, it would be equal to, of course, normal ordering of them. but with, again, some functions. Before, for each vertex, we have assigned only just one variable. Of course, it commutes with itself. But now we somehow replace our manifold by loops to this manifold. So for each vertex, we assigned infinitely many variables. And after quantization, there is no reason to assume that they're commutative and actually natural choices here. Okay. So the first new feature, which you see here, is weights, which we assign to all ages. Yes. 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 Normal ordering is just normal of these bosons. Yes. Yes. It's commutative. This is normal ordering, yes. I said you can ignore normal ordering if you're not familiar with this, but in these formulas, now this formula becomes meaningless. So just ignore these formulas. Or if you want, you can replace these formulas by formulas like this. The commutator of an and bm is equal n, p minus n, q in power minus 2n minus 1, delta n plus n, 0. So this normal ordering between A and B are equivalent to commutation relation between the Heisenberg algebras which correspond to the vectors.
What is the relation A and A?
No, it follows from this. It will be something like q minus 2n minus q minus n plus 2 minus q in power 2n. Perhaps sign. It is not written in my notes, so written. Yes, exactly. Now you can write the left side also. This relation. Okay. Is there no more questions? I want to. So first thing which I wanted to comment was about these weights of the ages, p. How essential they are, and they're essential, but up to some extent. So first of all, there is. Okay. First of all, there is a group of there is certain gauge. There are certain gauge transformations of these weights. Namely, if we write namely, if we have some vertex, we assign to it some current, we can always replace just the variable z here by a of tz. Since we already live in Q world, and we are okay with having poles and not on just standard diagonals, but on shifted diagonals, there is no reason to prefer some choice of the variable. And this really corresponds, and if you look to these formulas, you see that here p appears near the variable of A, and here also p appears near the variable of current A. So such transformation corresponds to the following gauge transformation. Okay, I don't know, to the following gauge transformation of the weights. So we have some vertex A with the weights P3, P4, P5. Why I started with P3? Unclear. Then this transformation would just rescale the weights of these ages. So outgoing ages will have additional factor t, and ingoing edges will have additional factor t inverse. So corollary of this observation that weights itself are not important. What is important are monodromy around closed loops. Actually, again, at least in the examples, reasonable examples which we consider, there is additional constraint. Examples which you consider, they come from some geometric perspective, like for Goncharov, and the quivers are usually drawn on some surface. And on some surface, we usually have some conditions. If you have local cycle, contractible cycle, then product of the monodromies should equal to q minus 2. And if you impose this condition, that essentially that your essential monodromies you have essentially correspond to fundamental this commutative homology group of your surface. So, for example, in this case, the only essential parameter is the monodromy around this cycle, and here is the monodromy around cycle around origin. This additional constraint. I supported this constraint by, saying that it happens in examples which we have, but the most naive argument is the following. So if you consider quiver like this, then in terms of zero modes, it means that in the adjusted matrix we have zero, so the corresponding variables commute. But now if you kernelize everything, whether they commute or not would now depend on their weights. And then it appears if you put weights p and q minus 2p inverse, make their product equal to q minus 2, they corresponding currents would commute. So this is a way in which you can cancel out such thing. Any questions? No, not for two here. So the question was, is it constrained only for cycles of length 3? But the answer is no. For example, here we have cycle of length 2, and also this constraint is good because in this way we can cancel. For any local cycle, if you have any phase on your surface, then monodromy around this phase should equal to q minus 2. Yeah. Okay, let me put it like this. This constraint which is satisfied in all reasonable examples. I think this is necessary for Laurent phenomenon, but yes. It's a matter of some conventions here. Your poles are shifted. In one direction you shift by q, in another in q inverse. In order to cancel, you should. Short, I don't know explanation. I have no explanation. Just maybe it's a matter of convention. Okay, I have like 10 minutes left. Maybe it's a good time to state some theorem. maybe not to state theorem, I need to repeat the draw again the quiver which I had draw on the left side, but still. So consider the following quiver. 1, 2. Okay, make it big. So again, this quiver is drawn on a cylinder, and we have horizontal arrows. And there are some arrows between frozen vertices, which I'm not going to define here. So vertices on the boundary are frozen, vertices inside are unfrozen. Okay, I forgot some red arrows. But up to now, this was a quiver just for before kernelization. There's no weights here. Yes. In principle, graph can be arbitrary. And in principle, graphs can be arbitrary. Better to have graph drawn on the surface, because on the surface, it's easier to work with this constraint. So this graph is drawn on a cylinder. Yes. And that graph was drawn on the, no, you know this graph. Okay. So up to now, that was the picture before kernelization, but now I have to put some weights. So I assume that use some gauge transformation to make all vertical weights equal to 1. Then I can make all horizontal weights to be the same, and they would equal to Q1, some number. And all diagonal weights will equal to some another number, which I denote by Q3. And these numbers satisfy Q1, Q square, Q3 is equal to 1. This is a condition for locality condition. So Q2 is Q squared. Just to ignore the problem with index up or down. And so the locality condition means that Q1, Q2, Q3, 1 this is equal to Q minus 2. Okay, theorem. Formulas like in example. Gives representation, and it's A of UQ GL3 toroidal in Wakimoto representation. I name this as a A, means that I plan to make B, but maybe before some comments are necessary. So here we have toroidal algebra. This corresponds to the fact which I mentioned before. I added additional frozen vertices here and here. But essentially, this would just add me some additional Casimirs, which in terms of test series correspond to evaluation parameter. So essentially, this evaluation representation. We have a map from toroidal to quantum affine, and then we take Wakimoto representation. But advantage of this picture is the following: that now we can, for example, glue this picture and construct representation of the toroidal, which are not irreducible representation of the quantum affine. More like product of evaluation representations is no longer irreducible representation of the fine dimensional algebra. Yes. For other types, I'm not quite sure about toroidal part. So I'm sure we'll get Wakimoto, there's quantum affine. But here, if you ask me, what was my reason to add the two vertices? I mean, for this picture, it's clear how to add them, but how to add them in the left picture, it's not quite clear. I mean, I know the answer, but I have no explanation. So I don't know about toroidal part. So you see these parameters like, so one parameter Q comes from quantization, and another parameter comes from this monodromy around this side, Q1. In terms of quantum affine algebra, if you don't like this toroidal, it would correspond to the level of your representation. Okay. And maybe it's good I can state B. This representation is mutation equivalent to known one. By known one, I mean some formals which are written in the 90s. This is new representation. I mean, as far as experts know, this is new representation. For example, this representation doesn't have good limit when Q goes to 1, differential limit. But in Q difference, well, and I don't. Yes.
When you say that doesn't have a limit, it means it doesn't have a good limit to developing algebra.
Yes. I mean, for quantum groups, there are two limits to Poisson and for developing algebra. Yes, and perhaps I confused. Yes, Poisson limits exist. Okay, and perhaps at this point you can ask, what is mutation? I haven't defined mutation in this chiral world. And my clock has disappeared. Maybe it means that I'm almost out of time. But I have my own clock, which says that I have 3 more minutes. So mutation. And as before, mutation consists of two parts. Combinatorial part, what happens with the quiver, and algebraic part, what happens with variables. And a combinatorial part you can easily generalize. So assuming that you have, say, A, B, C, the same quiver as above, you do mutation, and you just draw the same quiver as above. Actually, you can ask what happened with weights, and but you can see maybe it's not combinatorial part. But for algebraic part, you actually have a problem. And problem is formula for C tilde. Formula for B tilde is okay, inverse. We can take inverse of the exponent. Sum of two exponents is also okay, but 1 plus QB inverse of the 1 plus vertex operator, it's unclear how to act. I mean, this is infinite sum. So there is no formula like this. Uh, uh, in, instead, you can view this as some sort of the system of equations. So maybe I will not write the system of equation, but I state its existence and state how the answer looks like. So here we have P1, P2, P1 inverse. This is Q minus 2, P2 inverse. And so mutation is up to some detail is a certain operator intertwining operator which may have X from Fock space which correspond to Heisenberg algebra B to Fock space which correspond to Heisenberg algebra called B. And since this is an intertwining operator, you can assume that it comes from some R matrix. And this is true. So this comes from R matrix for toroidal GL1. So if you have start with a vertex which have loop to itself, this is literally Maulik-Okounkov Q-deformed R matrix. Or better to say, analog of the Liouville reflection operator, because now I act in one Fock space. And here, this is like more simple analog of the Maulik-Okounkov R matrix. So this is somehow correspond to GL2, and this is a GL1/1 analog of the Maulik-Okounkov R matrix. So formula which I wrote here, they're partially not true, partially don't have make sense, but it can be replaced by some avatar from the mutation theory. Okay, I have more or less 0 minutes, so maybe it's good time to give you a plan of my talk. So keywords which I haven't mentioned are screening operators and maybe from the mutation theory point of view, this is the main meaning of what's going on. So the combinatorics of the screening operators can be traded to combinatorics of the cluster varieties. This is technically what's going on. I haven't told you about any geometry, like surfaces and so on. For example, you can ask me whether pentagon identity holds for these mutations, and it holds in something. It holds in terms of projective space sense. It's not identity, it's just transform. And we have something like Fock-Rossley Poisson brackets, and so on. And maybe the very last thing which I write. Okay, maybe I say in words, and if somebody asks me, then I'll write it on the board. In words, say the following. So one can ask, what is the reason? Why should I expect that some cluster varieties should be, even quantized, should have this kernelization? And of course, I don't know, but this is similar to the another known story that this cluster varieties for which we have this kernelization, they appear as Coulomb branches of 4-dimensional series. And for Coulomb branches of 3-dimensional series, there is very similar story that these Coulomb branches are associated varieties for some vertex algebras. And this is Q deformation. So instead of Coulomb branch of 3-dimensional series, we have 4-dimensional series, and instead of vertex algebra, we have Q vertex algebra. Right?
Are you done? Thank you so much for the talk. Okay, will there be any questions about the plan for the talk?
So one of the main advantages of cluster algebras is that if you have a Poisson cluster algebra, which is a relatively simple geometric object, then there is an automatic way to quantize it. Is this also the case in the chiral cluster world?
I don't. So here I already worked with quantization. Already started with quantization. So can I say that what is a good property of the corresponding Poisson bracket which appears in the limit? Maybe I don't know who would answer.
But usually it is hard to quantize things.
Yes.
Usually, I mean, in particular, in this quantum affine algebra theory, it's usually hard to quantize things because you have to kind of invent formulas. So Drinfeld made this great discovery of Drinfeld new realizations, which is really behind all this thing.
Yes.
But cluster algebras, quantization is a algorithm. So I was wondering if you could make this algorithm chiral, so to do it in the chiral world. Because Poisson story is much simpler.
Pasha is asking, do you have a Poisson analog of this?
Yes. We have Poisson analog of this. Yes. There is. Okay, I'll have to think. I'm out of time. No, good. Yeah, I have to see. Yeah, I see question. Yes.
Yeah, I think. Okay, one question.
What is the precise? Do you have a more precise statement about this relation with Coulomb branch and this Q vertex algebra?
What's precise statement? So
the kind of statement I have in mind for 3D was that the one you said for associative variety, and after you quantize, what the statement would be?
I don't know whether a notion of associative variety exists in this Q-deformed world. But so the statement that the variety which we chiralize appear as a column branches, it is either theorem or definition of what is column branches. So in BFN case, if you start with BFN definition, then it is. I mean, there are theorems that the corresponding column branches have cluster structure, and they heavily intersect with the cluster variety which we chiralize here.
Okay.
But I'm not sure about name of the straight variety.
We need to stop here because we have the next talk without any breaks. But thank you so much for the talk and the answers. So the next talk now, without breaks. Well, 1 second to breathe. And maybe another second or two to set up our Zoom because it's an online talk. How good that you know. Yeah, it's on. There was something blinking. Where's the tech support? There.
Okay. Is it hello? Is it coming through?
We don't have the image on the screen yet, so we need a few on the big one. I mean, we need a few seconds to turn on the projector. Now it's on. It's Yes, now we see you also on the big screen. Okay.
Excellent.
So that's our next speaker, Thomas Bothner, and he will talk about what is a Riemann-Hilbert problem. Many thanks.
Yes, thank you. Thank you for the introduction. Thank you for having me. I'm sorry upfront for not being with you in person. It's a few days from now. I'm hosting my own conference here in Bristol, and it's hard to be in these two different places at the same time. But nevertheless, I'm extremely grateful for the opportunity to contribute, at least virtually, to the exciting summer workshop that is, just started. Now, what I've prepared is very much a survey talk. It is intended for newcomers to the field, not for experts, and I'm simply trying to answer the question, as on the slide, what is a Riemann-Hilbert problem? So what I will do is I will take you on a little historic excursion, trying to first pin down what I would call first occurrence of a Riemann-Hilbert problem in mathematics. Then I will tell you what kind of work was done back then on the same problem, and then we will see that very naturally out of this work a beautiful analytical apparatus grew, which nowadays can be summarized under sort of an umbrella of Riemann-Hilbert techniques. And then I will showcase that same bag of techniques with 5 examples. They are all coming from the theory of integrable systems, very much aligning with the topics, with the focus points on this workshop. That's more or less the idea. If there's any questions whatsoever along the way, just stop me and let's chat about the questions. All right? All right, so to begin, if you are an expert in this field, and of course many of those are in the room, the answer you probably know, but if not, then perhaps my answer to the question, what is a Riemann-Hilbert problem, is not what you might think. In fact, one can make a point, and this point has been made, that the first Riemann-Hilbert problem occurred 125 years ago in 1900. This was the Second International Congress of Mathematics, famously held at Paris, and Hilbert, during one of the sessions, he gave his address, and he came up with a list of problems for the 21st century. 23 of those, many of those very famous problems, very hard problems, we'll be interested in problem number 21. So Hilbert did a curious thing. He first published his problem list in German, not in the French proceedings of the Congress, and this here is copy-paste from his German publication, so I will translate. This is problem number 21. It's about proof of existence of linear differential equations with prescribed monodromy group. Now, the terminology already appeared in the previous talk, right? Monodromy appeared there, but if you're a newcomer, I will define it later on precisely, all right? Before doing that, let's read on a little bit what he says here. So he says, well, it's a problem in the theory of linear differential equations. He says, or he claims, that this problem is probably something that Riemann already thought about, and the problem consists in showing that there is always a linear differential equation of the Fuchsian class with prescribed singular points and prescribed monodromy group. Okay? More to the point, he says the question or the task asks us to find n functions in the variable z. Those functions are, well, regular complex analytic in the complex z plane away from the singular points. In those singular points, the function can become infinite of only finite order, and as you continue the function, along a loop around the singularity, it changes via the given monodromy. Right? One can make a point that this is really the very first Riemann-Hilbert problem. Why? Well, because Hilbert formulated, and he, well, clearly mentions Riemann up here. Although, if you're honest, I don't think you can find any papers of Riemann where he actually thinks about, a problem of this type. But nevertheless, I will follow this convention. This is also a convention that was pinned down by Anosov and Bollybruch. Andrei Bollybruch is a player that will appear frequently in the first half of my talk. They wrote a nice book about Hilbert's 21st problem and also follow the logic that we should call it the original Riemann-Hilbert problem. It is definitely a problem in the space of Riemann's ideas because Hilbert asks us to construct, well, a function globally from given local data. Right? So this is definitely a theme very much present in Riemann's work on complex analysis. All right, so that's the original Riemann-Hilbert problem, Hilbert's 21st problem. Now, 125 years have passed since then, so it's only natural to ask whether it has been solved. And their curious thing seemingly happened. If you look up, this is from Wikipedia, 21st problem, the answer is, well, partially resolved. Even better, you can choose your answer. Yes, no, open, depending on more exact formulations of the problem. So that something very curious happened. Hilbert, he was vague in the formulation of his problem, perhaps surprisingly vague. And this wasn't a language barrier. So I'm German, I read the original text in German, it got then translated into French and English, and that didn't add to the confusion. The confusion was already there in the original German language. And what type of confusion could that possibly be? Well, let's think about this for a moment. So he says, given monotony group, given singularities, he wants us to realize it by what? Well, one way you could do it or attempt to do it is by a Fuchsian linear nth-order scalar differential equation, right? Now, that's one way you could think about it, because he never uses the word matrix system. Now, on the other hand, Hilbert uses this peculiar formulation of saying that the functions that we are, well, that he wants us to find, they can only become infinite of, at most finite order at a singularity. By doing that, he actually never mentions the terminology of a Fuchsian singularity explicitly, right, which is nowadays standard terminology in ODE theory. What he actually refers to is a so-called regular singularity, and there's a big difference between these two types of singularities, as I will show you later on with example. Right? So one way you could interpret it, case 2, does he want us to look at linear systems having only regular singularities, or because he mentions Fuchsian class, is he actually talking about honest Fuchsian systems on the whole Riemann sphere? Right? So these are three possible interpretations of his problem, and depending on which one you choose, the answer to his question is different. Right? It was already known at the time of the Congress that in case 1, thinking about scalar nth-order equations, the answer is negative. So he was almost certainly not going that direction. The answer is negative because Poincaré monotony representation.
Stop.
Which we'll talk about. Yeah.
You have to go back like 30 seconds because your picture was frozen.
Oh, I'm sorry. What was the last thing you heard me speaking about?
That Poincaré did something. That Poincaré did something. And then you got frozen.
Okay, let me move the computer. Maybe my internet is not
the last words were according to Poincaré.
Okay. That I was pretty much there. So, case 1 of the interpretation of Hilbert's 21st problem, there the answer was known to be negative already at the time when he formulated the problem, because Poincaré, prior to the Congress, he had counted the number of parameters in a Fuchsian linear scalar nth-order equation, and that number is strictly less than the dimension of the admissible monotony representation. So that is not what Hilbert was thinking about. Now, case 2, that was very influential for the development of the modern theory of Riemann-Hilbert problems, because Josip Lemay was a Polish mathematician. In 1908, he published 2 papers, And in those two papers, he almost solved Hilbert's 21st problem. He solved it, although only in the context of regular singularities, but he himself, I think he claimed that he had actually solved it for the Fuchsian case too, but that turned out to be wrong. Nevertheless, the almost solution of Hilbert's 21st problem for Fuchsian systems by Plémé was very influential because of the techniques that Plémé employed, and I will tell you those techniques later on. Anyways, I already said there was a mistake in Plémé's work. He was not aware of it. He passed away in the late 1950s, and in 1989, André Bolybrug, he came up with first counterexample for Hilbert's 21st problem in the Fuchsian interpretation, so an interpretation 3RP. So the answer there, if you choose the third case, is just negative. So Hilbert got it wrong, right? Because he was saying it should always be possible to achieve that, but no, it's not. Okay. So, now history aside, let's become a little bit more concrete. So let's introduce some background terminology. It's very simple, very basic stuff. We'll be dealing with p by p linear systems of differential equations in the complex plane, so Z will always be complex. Psi is the unknown p by p matrix, A of Z is the coefficient function. To remind you of some basic things in that theory, if you start with coefficient matrix A, which is analytic near point Z0, then the method of successive iterations yields existence of a fundamental solution, which is also analytic at the same point. This is the Picard-Lindelof theorem that we all know. It's actually easier to prove it, to establish it in the complex setting, because the sequence of iterates, it converges uniformly, and then if you start with something analytic, a sequence of analytic things, you have uniform convergence, the target automatically is again analytic. And that's not the case when you're on the real line, right? Alright, however, we will be interested in differential equations with singularities, so necessarily we have to move to the Riemann sphere with n punctures, so the AJs, these are n distinct points, and you enforce analyticity of the coefficient matrix away from those. Then, you're starting with a local fundamental solution. The monodromy theorem famously guarantees that you can continue any such fundamental solution along any path on the sphere with punctures, and even better, the continuation only depends on the homotopy class of your path. Alright, now, having that under our belt, now let's move to finally define what we call monodromy, and this will turn out to be a representation of the fundamental group, as many of you are of course aware. How to do it? Well, you fix base point A0 of your somewhere on the surface as base point for the fundamental group, and then you start with an arbitrary fundamental solution psi, and you continue it along a loop. So pi 1 S A0 is just first homotopy group, and once you do this continuation exists by monodromy theorem. Once you have done it, you obtain another fundamental solution to the same equation, right? Call it psi tilde. But since both of these are fundamental solutions to the same linear homogeneous equation, they have to be related by invertible multiplier, right? This is what is written here. The G of gamma is the invertible multiplier, depending on the loop that you choose. However, it's actually not dependent on the loop itself, because as I said earlier in the monodromy theorem, it only depends on homotopy class. So actually what you have is a well-defined mapping from the homotopy class of such a loop to the corresponding invertible matrix G sub gamma. And this is a representation of the fundamental group. Alright? Here's the picture. So the singularities I drew down there at the bottom, A1, A2, In. The base point here on top, A0, different from all the singularities. And then the continuation is carried out along those what I will call fundamental loops. So the red loops, gamma j, the jth loop just wraps around one's singularity aj and not around any of the other singularities. As you can see, because of the geometry, because S is path connected, in particular, if you not just path connected, that's beside the point, but if you compose gamma 1 with gamma 2 all the way up to gamma n, then that loop, that composition loop, is homotopic to the trivial loop, right? Because of the geometry of the surface. Alright, fantastic. Now what are the monodromy matrices? Well, those are just the matrices that come from the image of the representation under the equivalence class of such a fundamental loop. We denote them by G sub I, and there's n of those because they got n singularities, and they generate a group which we shall call the monodromy group. Now, up to this point, there's still some ambiguity in the game that should be clear, because I said earlier we start with an arbitrary fundamental solution psi, and we choose an arbitrary base point for our fundamental group. So what happens if you start with a different fundamental solution? What happens if you start with a different base point? Well, that is well known. The corresponding monodromy matrices were, provided you start with a different choice, they are related to the original ones by conjugation with invertible matrices, right? This is here again on the level of the fundamental solution because you're looking at a homogeneous linear system, and when you start changing the base point, because now this is because of path connectedness, the corresponding fundamental groups, they are isomorphic, right? And that isomorphism translates into the fact that the corresponding monodromy matrices, they are related by conjugation with invertible matrix. So in other words, what I'm aiming at is that you should really be thinking of monodromy as an element of this space here, right? So conjugacy classes of representations of the fundamental group, where you quotient out the general linear group. Okay, very good. Now, instead of thinking about maps, instead of thinking about representations or conjugacy classes thereof, you can also think about sort of more down-to-earth matrices. So there's an isomorphism of this curly M up here to that thing down there. So n p by p matrices, G1 up to Gn, they have to satisfy what I will call cyclic constraint, because I said earlier the fundamental loops, they compose to the trivial loop, the homotopic to the trivial loop, the composition of all n of them, and that simply means that all these n matrices, they have to multiply together to the identity matrix. This is perhaps a little bit easier down here because you can now count the dimension. You can very easy count because you got n matrices of size p by p, so you got n times p squared many parameters, but then you got this one matrix constraint. So this enforces p squared many equations, so you got n minus 1 times p squared many variables, and then you have to quotient out, and then you subtract minus p squared minus 1. This is a number to keep in mind, n minus 2 times p squared plus 1. All right, one thing remains to be defined, Fuchsian singularities. All right, well, system is a Fuchsian system if all its singular points are first-order poles. And here, without loss of generality, we shall assume that those n singular points, they all lie in the finite part of the complex plane. This you can always achieve by some Möbius map. And as such, if all the singularities are in the finite part, in particular the point at infinity is not going to be a singularity, and that is equivalent to this constraint here on the right, that the sum of the residue matrices is the zero matrix, right? So that zero is p by p matrix. Very good. Now we have everything in place to give precise formulation of the original Riemann-Hilbert problem in the Fuchsian setting. It is simply a question about whether the so-called monodromy map is surjective. So what is the mapping here? What's the codomain and the domain? Well, the domain we've already defined. This is the monodromy, right? Conjugacy classes, representations, and on the left is something which I will call M star. It's written out here. So n tuples of p by p invertible, not invertible, n tuples of p by p matrices, which sum up to 0, again quotient out by general linear group. If you do the counting here once more, that thing has the same dimension as the curly M on the previous slide. So that might indicate that this is perhaps a bijection. Well, it's not. So but this took a long time. So this is André Bolybrug's great achievement of 1989, that although the dimensions here match in general, this map is not surjective. And I will get to that. Okay, now let's first look, however, at Plemay's almost solution to this problem. So Plemay, 1908, he published solution, or he claimed it to be a solution, and it was accepted by the community for many, many years. For almost 8 years. What he did is quite curious. So he reduced the original Riemann-Hilbert problem to a problem in the theory of integral equations. So this was very much an analytic solution or an analytic approach to the problem. He used state-of-the-art stuff. I mean, state-of-the-art meaning back in 1908. So Fredholm had developed theory of integral equations maybe 10 years before that. Hilbert had worked a lot on singular integral equations. So Plémé came about with tools like the Fredholm alternative, Riesz-Schauder theorem. All of this is very standard nowadays in our classes, but back then in 1908 it was really state-of-the-art stuff. All right, so what did he do? Well, what is the Hilbert boundary value problem in his work? Well, here's a picture. So you start with the n singularities, that's the data which is given to you, so you know the singularities and you know the monodromy matrices. And again, we assume all of them to be in the finite part of the plane. These are the black dots in my picture. Now what he did is he connected them by a simple closed contour, say, these straight lines here. The fundamental loops are again indicated in red. And then he defined on the curve gamma a piecewise constant matrix-valued function. And the value of that function is indicated here in red. So on the segment from A2 to A1, you want that function to be equal to the first monodromy matrix, G1. Then on the second one, you multiply G2 onto G1, and that's how you go all the way around. Keep in mind, the monodromy matrices, they have to satisfy a cyclic constraint. They have to multiply to the identity. And that means in turn, on the last segment here, from AN to A1 or the other way around, you have the identity matrix as value of your piecewise constant thing. I've oriented the contour, as you can see, so there is the arrow. So as you traverse in the direction of the arrow, what I will use is I will say that the side to the left is the plus side and the side to the right is the minus side. And as you can see, the contour, it now partitions your complex plane into two domains. There is the exterior, this will be called C plus domain, it contains the point at infinity, and then there's the interior, which contains the base point A0 of the fundamental group. This will be called C minus. All of this is written out here, what I just said in Word. Now, what is the Hilbert boundary value problem? So here for the first time it comes in a blue box. It asks us to determine a pair of matrix-valued p by p functions, y plus and y minus. Y plus is meant to be analytic in the exterior region, C plus, y minus analytic in the interior one, C minus. Besides the analyticity in those domains, you require continuity down to the contour, but away from the n singular points. Right? That's constraint number one. Constraint number two, on the line segments away from the endpoints, you require y plus and y minus, right? So they are continuous down to the contour, but their values need not match as you come from the outside and go to the inside. What is the constraint is that those values have to be related by this constraint, the jump constraint, and that constraint precisely involves that piecewise defined thing, which is written out here in terms of the monodromy matrices. Call it G of Z. Okay. One thing remains, or perhaps two, depending on how you count. You have to enforce some singular constraints near the singular points. So y plus, y minus, depending on how you approach the singular point, is meant to stay integrable in this sense. So y plus minus z times z minus ak to a power kappa, strictly less than 1, supposed to go to 0 as z creeps up to ak. And this is to be understood in a non-tangential fashion. So you creep up to the singular point either from the outside or from the inside, but in a non-tangential fashion. Okay. Also at infinity, you have to enforce a certain normalization. It is written out here. So y plus, because we are outside, we're shooting off to infinity, multiplied onto by z to the d being a diagonal matrix with integer entries, is supposed to approach the identity matrix. Okay, that's the problem. This problem is equivalent to a system of singular integral equations. I don't write out those integral equations because actually problems of this type with 3 or 4 conditions we will see later on again. That's why I choose this approach. Now what did Plémé do? Well, he first proved this problem has a solution. And for that he used abstract reasoning, Riesz-Schauder theorem and Fredholm alternative. And now, how does the solution to the same problem actually relate back to the Riemann-Hilbert problem? Well, here we go. He took the solution which exists by abstract reasoning, multiplied onto it z minus a1 raised to that matrix D, which appeared at the normalization at infinity, and calls it psi. And then he proved this is a simple enough calculation. The same psi satisfies p by p system of differential equations. And R of z coefficient matrix is actually rational, with poles precisely at the singular point, and even better, the monodromy generated by the system, 2, it exactly is equal to the monodromy that you come with. So the monodromy group is generated by the same matrices G1 up to Gn. So that's great, because now you're almost there. But now, of course, the devil is in the detail, because these poles here, they need not be of order 1. So in other words, this system need not be in general a Fuchsian system. And that's where he went off in a sense. He realized, however, that this system is foremost a regular system. So now it's a good time to define what are regular systems versus Fuchsian systems. Well, regular system is a system of the type 1, where all the singularities are regular. So what does this mean? Any solution of a system at such a singularity has at most polynomial growth in the vicinity of it. Okay? Now, is there a difference between Fuchsian singularities and regular singularities? You probably know the answer. Well, if you are in the scalar world, so p equal to 1, then actually they are the same. So Fuchsian singularities for an nth order scalar differential equation and regular singularities, they are exactly the same things. But this is no longer true if you go to matrix systems. If you go to matrix system, simple enough, example written here, look at this guy. So this has a regular singularity at z equal to 0. You can check for yourself. There's some multi-valuedness, but okay. Take care of it with some branch convention. And now if you just formally differentiate this guy, you will find out it satisfies the system written up here. And there you see z equal to 0 is a second order pole. So this is not a Fuchsian system. Now Plémé, he was aware of that. He was aware that Fuchsian systems, they form a proper subclass of regular systems. But he wanted to solve Hilbert's 21st problem for the Fuchsian system. So what did he do? Well, he applied a series of transformations, explicit transformations. You can read them in his paper. And those transformations, they fix the singularities, they fix the corresponding monodromy, but they change regular singularities to Fuchsian singularities. And he falsely believed he can do that for all n of those singularities. But that's not true. And he was not aware of that thing. You can achieve it for all except perhaps one of them. But this is a theorem that was written down many years after he had passed away. So this is Ilyashenko, Treibig in the early 80s. If you put an additional constraint in the game, in that one of the monodromy matrices is diagonalizable, then actually Plémé's transformation trickery, it works for all the singularities. And in that scenario, Hilbert's 21st problem for Fuchsian systems has a positive solution. But if this is not the case, then unfortunately Plémé was wrong. He was not aware of it. Nevertheless, I want to formulate a positive result that came out of his work. And this is the Röhr-Plémé theorem. Plémé published it in 1908. I read his paper. This is in German. It's quite tough, to follow. He then wrote a book in 1957, and this is very much from the book. So any matrix group with n generators satisfying this constraint that we saw earlier, it can be realized as a monodromy group of a regular system on the sphere, having all singularities Fuchsian with at most one exception. And that is definitely a positive result that he proved rigorously already in 1908. He was wrong in claiming that he can reduce all of his singularities to Fuchsian ones, but that he didn't realize. Okay, anyway, so now let's switch gears slightly. Well, let's move on further down the timeline, so to speak. So Plémé had published this in 1908. The community had accepted it as a positive, affirmative solution to Hilbert's 21st problem for Fuchsian systems, and henceforth the community focused on other aspects when it came to this particular problem. So they tried to make things more explicit and more concrete. It started with Birkhoff. I didn't even put his name on the slide in 1913. Birkhoff simplified Lemay's argument, and in particular he generalized it to systems of difference equations. There you can ask very similar questions. By the way, Igor Krycheva, who will be celebrated in this workshop, he has written papers about monodromy of systems of difference equations and associated Riemann-Hilbert problems. I will not look at difference equations. Instead, what I will focus on concerns foremost differential equations. So in that area, Lapo-Danilevsky in 1929, he came up with an almost constructive solution to the problem. He used power series and inversions thereof, but that only works for monodromy matrices sufficiently close in some sense to the identity matrix. Very nice stuff, very much special function related work was done by Krylov in Erugin 56 and 83, but that concerns now 2x2 systems with 3 or 4 singular points. This Krylov business, it deals with Gauss hypergeometric functions, and the case with 4 singular points is very, very nice, very interesting, because it relates to Poincare-Levé special function theory. So Poincare-Levé 6, the Hilbert 21st problem, for 2x2 systems with 4 singular points, it relates to Poincare-Levé 6. And I mention this because later on Poincare-Levé functions will appear. What else? Well, besides of making, or next to making things more explicit, more concrete, of course, people started generalizing Hilbert's 21st problem, going away from the Riemann sphere to more sophisticated surfaces. All of this can be done. It requires, though, a very different approach. This is foremost geometric stuff. This was done by Röhrl first in the 50s. Pierre Delain contributed prominently to this area. Nowadays, all these beautiful generalizations to surfaces, they go under the name of Riemann-Hilbert correspondences. I will not touch upon those. Instead, I will tell you now a little bit about, well, the ultimate negative solution given by Bollybruch, further simplified by Kostov in those 3 years. Bollybruch's work was very, very beautiful because he gave necessary and sufficient conditions for the solvability of Hilbert's 21st problem on the Riemann sphere. So what are some of those things? So here's the Bollybruch-Kostov theorem, 1989. So this is, 89 years after Hilbert's address. So they prove that once you come about with irreducible monodromy representations, those guys you can realize by Fuchsian system on the sphere. So that's a positive result. But if you drop the irreducibility, then there indeed are certain reducible monodromy representations which you cannot realize by Fuchsian systems. And Bollybruch gave an effective recipe to construct counterexamples. The first one was a 4x4 system with 3 singular points. So as it so happened, Hilbert got it wrong. I already said this earlier. The original Riemann-Hilbert problem in the Fuchsian interpretation cannot work out. We cannot always realize a given monodromy group by a Fuchsian system on the Riemann sphere. Very good. So now, Andrei Bollybruch did this in 1989. He then lectured on those results, also at an international congress of mathematics, but this was 1994, so 94 years after Hilbert. He then sadly, soon after, he passed away. Anyways, now, what I will do now is I will follow developments tangential to Lemay's work, because he used analysis in his almost solution, and the techniques that he used, they actually showed up reappearing in problems related to integrable system techniques, right? So, but this was in the 1960s, 1970s, and now I will walk you through some of that history. That really, those problems, they gave rise to Riemann-Hilbert factorization problems and a whole toolbox around them. And then this is quite interesting stuff, I think. All right, so it starts though historically, again in the 19th century. There's the famous Sommerfeld diffraction problem. This is from 1896. Sommerfeld is a problem in wave mechanics. I will tell you a little bit about it. Sommerfeld came up with a solution, but I will use a different approach to it, an approach that really requires the study of Hilbert boundary value problems. And that's Wiedenhoff method, right? So Wiedenhoff, this is in the 1930s. So here's the problem. You have incoming train of plane waves indicated as orange, arrows, and you have an infinite barrier here on the positive x-axis, right? So that boundary constraint, you can see immediately what will happen. The waves cannot pass through it. So here on the right, you will have a region where reflection happens, and you will have a region which is always in the dark, right? Because the rays cannot pass through it. So now you come with a wave equation in 2 dimensions, and you try to solve the associated boundary value problem. How do you do that? Well, first off, the wave equation, so-called Helmholtz equation, is given here. There's some wave number k0 squared involving and some boundary condition. I'm very vague about it. I don't even show you the boundary condition. All I will do about this problem is I will tell you, if you use Wiener Hopf techniques, you go to Fourier variables. In those Fourier variables, the PDE with the boundary condition, it will become an integral equation. And the same integral equation, as an integral equation of Wiener Hopf type, is equivalent to a Hilbert boundary value problem. That's the only thing I will say about it. I won't show you the same problem. I do this because of historical reasons. I think really this Sommerfeld diffraction problem was the first problem in mathematical physics where Hilbert boundary value problems can be used efficiently for the solution of the problem. That's why I mentioned it. Now I will say much more about the integral systems revolution that took place in the 1960s and the 1970s, and again, Igor Kryucheva, he contributed famously to this area back then. So what happened? Well, there were first some numerical simulations carried out by Fermi, Pastur, Ulam, and then Gardner, Green, Kruskal, Miura developed a method, the inverse scattering transform, that allows you to solve certain PDE initial value problems. Many other important people contributed to it then over the years. Peter Lux, Vladimir Zakharov, of course, famously, discovery of complete integrability of defocusing NLS. And that actually is the equation I will use to showcase the Hilbert boundary value problem. So defocusing NLS is written out here. There are many other equations, of course, where the same scheme applies, but there's no time for that. So let's focus on defocusing NLS, written out here, and the initial value problem. So you start with some simple, nice initial data from the Schwartz space, say. X is space, t is time. All right, so how do you solve this initial value problem? Well, these people, these gentlemen, have showed us how to do it as a first step, which involves the calculation of the so-called reflection coefficient. Now, there's not much wiggle room in this, because if you start with Cauchy data that is from the Schwartz space, then there's a bijection to the class of reflection coefficients in the same function space, and moreover, functions or reflection coefficients with supremum norm strictly less than 1. This is a famous result by Beals and Koifman. It's the so-called direct scattering transform. Only very rarely will you actually have a formula for the R of Z, right? So you come with Y naught, and then you try to calculate R of Z. Only rarely you have a formula for it, but that's okay. You have very nice analytic properties for R of Z. And having those nice analytic properties, Zakharov and Shabbat then showed how you can now construct solution to the PDE initial value problem. And it goes through the inverse scattering transform, which is most conveniently formulated again as a Hilbert boundary value problem. So that's the third one that we now encounter, the Zakharov-Shabbat problem. It asks you to find matrix value function x, 2 by 2. The characterizing properties are formulated in terms of a spectral variable z, but because there's a PDE somewhere in the background, x and t, they enter as parameters. And then, as it was for Plémé back then, you enforce certain conditions on x of z. Analyticity somewhere in the plane away from some contour. Earlier for Plémé, it was this polygonal path joining all the singularities. Now it's simple, it's just a real line. And we again impose continuous extension down to the real line. Then on the jump contour, as it was earlier for Plémé, we have some jump constraint. Here it is written. It looks perhaps a little bit more complicated, but methodologically the same thing is happening again. X plus and x minus are related by this jump constraint. And that jump constraint encodes the Cauchy data through the reflection coefficient, and it depends on the parameters t up here and x here to the right. Lastly, some normalization at infinity, exactly how it was for plane A. Now, how does it relate to the PDE initial value problem? Well, if that problem is solvable, which it often is, then if you look at this coefficient here, x1 at infinity, so this is an expansion enlarged to z, meaning x1 is independent of z, but it depends parametrically on x and t, and then up to 2 times the imaginary unit, that same coefficient, it's 1-2 entry, it will solve your PDE with the given initial data. Right? So that's how it works. Okay, next example, the third one in my list. Besides PDEs, there are ODEs, some of which are very important in mathematical physics. Now, in the early 1980s, a new method came about, the so-called isomonodromy method, developed more or less independently by 2 groups, Jim Momiba Ueno in Japan and Flashka Newell in the United States. I also mentioned Leningrad gang around Alexander Itz, Viktor Novokhanov, Andrei Kapayev, Alexander Kitayev, because they really matured the theory, and I will walk you through one of the aspects of the same theory. I will focus on a particular Barnley equation, the second one which is written out here. It's the second one in a list, as you know, of 6 celebrated Barnley differential equations. And for simplicity of the argument, I will be focusing on solutions that satisfy this additional constraint that just says that the solution is supposed to be real valued on the real axis. Okay, so how do you solve? Now, careful with this word, that's why it's in quotation marks. So, of course, U identically 0 solves this thing, but there's a hard theorem that says, you know, any other non-trivial solution you cannot construct in terms of classical special functions and finite number of contour integrals thereof. So what do I mean by solve? Well, we will rephrase Barnley 2 again in terms of the Hilbert boundary value problem. And here's the construction. We define Stokes data, 3 parameters as 1, 2, 3 that satisfy this constraint. This constraint you should link to the constraint that we had earlier in Clémé's work when all the monodromy matrices multiply to the identity matrix, right? So this constraint you can now count a little bit. This makes this generically a 2-dimensional manifold, and that is okay because I'm looking at a second-order differential equation, so there should be 2 degrees of freedom, right? These last 2 constraints here, that S1 is complex conjugate of S3 and S2 is real valued, they are not essential. They are here because I'm looking at these solutions which are real valued on the real axis, right? And in fact, if you have this constraint here, these additional 2 constraints in place, this guy here is generically a 2-dimensional real manifold, okay? All right, excellent. Now, coming with this data, this is our monodromy data, our Stokes data. We define 2 by 2 matrices, the Stokes matrices. They are lower and upper triangular. There are 6 of those, but you know I have only like 2 parameters, well, so that there's some relation enforced with those. So they are lower upper triangular depending on your index, and then again you look at a particular Hilbert boundary value problem. I write it here as the Barnley 2 problem. It again asks you to find something matrix valued. The characterizing property are written out in terms of a spectral variable, but since there's an ODE this time in the background, there will be parameter x somewhere. Problem is written out here. We don't need to bother ourselves with the technicalities now anymore. You can clearly see that the same methodology applies that we had earlier for the defocusing NLS and previously for Clémé's solution of Hilbert's 21st problem. Analyticity somewhere away from a contour, here is those 6 rays, continuous extension in the sectors in between, jump relation on the rays, and normalization somewhere. That's the only thing you should take from this. The precise structure here doesn't matter, right? What matters is a result by Bollybruch and Kapayev and Itz that for admissible choices of Stokes data, this problem is meromorphically with respect to solvable, and here is Barnley 2 solution hidden. So again, you look at that x1 coefficient at infinity. It's independent of z, but it depends on the parameter x, and it also depends on the Stokes data s that we start with. That coefficient is 1-2 entry up to a factor of 2. It will solve your second Barnley equation. Okay? This is not a coincidence, not at all. because there's a second part to this result, that in fact any solution to the second Pauli equation can be characterized in this fashion. So there's a bijection between solutions of Pauli-Levi-2 and that monodromy manifold M. So in other words, this bijection allows you to parameterize solutions to Pauli-Levi-2 in terms of monodromy data. And this is very convenient to do, especially for application. Okay, next application, more in math physics, quantum integrable systems. There's this famous JMMS paper of 1981. Bogolyubov, Iselkin, Korepin wrote a book. Alexander Itz, also a major player back then. I will just focus on one example. I'm not attempting here to give lecture on quantum integrable systems. One example is a Heisenberg antiferromagnetic model, the spin 1/2 XY model. There is a Hamiltonian on a suitable Hilbert space with Pauli matrices. We don't need to know the details. I'm advertising here Hilbert boundary value problems. So where do they enter in the study of this model? That's more the question I would like to answer. Well, this is an exactly solvable integrable model. You can calculate certain correlation functions, one of which is the so-called autocorrelation function. And that guy admits a Fredholm determinant representation. This is the formula written out here. So DET is the Fredholm determinant of an integral operator, K sub t, on this space, and the kernel of K of t is written out here on the right. Now, Fredholm determinants in general are highly complicated objects. They're highly transcendental functions, say as a function of t. So how do you actually calculate them efficiently? Well, as it happens, you can recast a Fredholm determinant in terms of a Hilbert boundary value problem. And here it is. Again, the details, they don't matter much. It's the same methodology that applies. Analyticity of a function somewhere on the contour, some jump constraint, and normalization at singular points and at the point infinity. Provided this guy is solvable, provided such a function x of z exists, then it relates back to the Fredholm determinant with this simple enough formula. So you take the logarithmic derivative of the Fredholm determinant, this is a function of t positive, then up to -2, this is precisely the 1,1 entry of this x1 coefficient. Right? So this is good. This is good. Well, okay, why is it good? It might not be so clear because I'm rephrasing right now, I'm paraphrasing an object which is highly transcendental in terms of a solution of a problem, and it's not so clear how explicit the solution of this problem actually is. But I will get to that later. Okay, last one, fifth example that I've prepared pertains to the theory of random matrices. There are some exactly solvable matrix models out there. Here is one, so n by n Hermitian matrices, and you sample them according to some probability measure, written out here. So what are the players? So M is your n by n Hermitian matrix, dm is just the product Lebesgue measure on the functionally independent entries of M, and then there's some Boltzmann-Gibbs weight here. So e to the minus capital N, n is another parameter. You could set it equal to the size, and then there's a confining potential V. For simplicity, as a first exposition, you can think of V of x equal to x squared. That will already be very nice. C is normalization, so that you have probability measure. Now, the study of such objects is very traditional, I would say. Physicists in the 1970s realized, Dyson-Godin-Mehta, that you can calculate various important statistical quantities in this model in terms of orthogonal polynomials. For instance, correlation functions you can calculate in terms of the Christoffel-Darboux kernel of a system of orthogonal polynomials. So here's the Christoffel-Darboux kernel written out. The polynomials are the p sub j's. They are orthonormal even with respect to this e to the minus n v of x. Remember, v of x is our confining potential. All right? Now, however, now comes the issue. So unless your v of x is very simple, for instance, v of x equal to x squared is simple, if that's not the case, then you don't have any good formulas for your orthogonal polynomials. Good meaning here formulas that allow me to carry out some efficient asymptotic analysis. Right? Because ultimately, you're interested in scaling limits of your correlation kernel. So what do you do if you don't have those formulas? Well, as it so happens, there is a way to characterize those orthogonal polynomials, again through a Hilbert boundary value problem. Fokas-Itzkitaev showed how to do that in the early 90s. Once more, need to find some matrix value function, analytic property somewhere, jump on a contour, and normalization at some points. That's it. If this problem is solvable, this, by the way, happens precisely when those polynomials exist, then the solution, that matrix function x of z, if you look at its 1-1 entry, that will give you the nth monic orthogonal polynomial with respect to this weight. Okay. So those were 5 examples now. But I already indicated I haven't really made a strong point why the Hilbert boundary value problem characterization would be any better than what I start with, right? So for instance, if you think about this spin chain model, Freitorm determinant, which is a complicated object, I rephrased in terms of solution of Hilbert boundary value problem. Yeah, but as it so happens, you're not able to write down explicit formula for that boundary value problem. So what have I actually achieved by this characterization, right? So I would now like to answer the question, so what? Well, that takes us back to Clément, so we come full circle. You can think, and many people do it, you can think of Hilbert boundary value problems as types of contour integral representations for your observables. And this really goes back to Clément, because what did Clément do? Well, he came about with a Hilbert boundary value problem, having its solution abstractly. He then showed it relates to a system of differential equations. So in other words, if you can link your observable to a Hilbert boundary value problem, then you are in a position to derive systematically dynamical systems for your observables. Clément did it first in 1908. And I mentioned Alexander Ritz in 1990 because he really stressed that point for the quantum integrable systems. Okay? But what else? Well, I mean, this is in complete analogy. That's why I use contour integral terminology here, because if you have a function as a contour integral, then it's easy to differentiate the guy. Right? And here, this very similar thing happens, but on the level of the Hilbert boundary value problem. Now what else? Well, contour integrals, they are amenable to asymptotic analysis. Right? There's classical stuff out there. Many books have been written about it. Well, it would be great if similar techniques exist for Hilbert boundary value problems. And they do. This took, 40 years or so to transpire. It started with Sergei Manakov, also Mark Ablowitz. They worked on the integral equations. These are Gelfand-Levitan type equations. The first people who seemingly work directly on the level of the Hilbert boundary value problems are again Itznov, Okshenov, Kapayev, and Kitaev. They used, however, WKB techniques for the asymptotic study of the Riemann-Hilbert problem. And those WKB techniques, oftentimes they require you to come with some a priori information about the asymptotics that you're trying to establish. And that's quite hard then to rigorously justify that a priori step. Fortunately, Percy Dave and Jin Zhou in 1993 came up with a better approach. It's nowadays called the nonlinear steepest descent method. That method goes through without any a priori information, and that is the nowadays go-to method, the Dave Zhou nonlinear steepest descent method. It's the go-to method if you're interested in pulling asymptotics out of a Hilbert boundary value problem. And I will show you 3 examples where this method has been successfully applied and what kind of results came out of it. Well, the first one takes us back to Poisson-Levé functions. They are the famous connection problems. They already exist for classical, differential equations, linear ones. So what do I have in mind? Well, we pick a particular solution family to Poisson-Levé 2. Poisson-Levé 2 I showed you earlier. I parameterize solutions of it in terms of the Stokes data, and here I make this particular choice. All right, that's the choice. That choice, in fact, corresponds to the Ablowitz-Segure family of solutions that was studied in the early 1980s. Now, it's not hard to figure out, for that you don't need to Hilbert boundary value problem, it's not hard to figure out that solution to Poisson-Levé 2 with that data behaves at plus infinity very much like every function. So it goes down to 0 super exponentially fast, but it is multiplied by the parameter gamma. Right? And gamma is non-negative real numbers, say. You can make this complex too, but here let's keep it simple. Let's make it non-negative. Now, so you know now how your solution behaves in one direction, and you know how it depends on the parameters. So now the connection problem asks you to construct asymptotics in a different direction and figure out how the parameters in that direction relate back to this gamma. So that's connection problem. And the answer is known for Ablowitz-Segou family, and it's a very rich answer. There are three qualitatively different cases. There's a case, gamma strictly less than 1, non-negative, where you have oscillations out at -infinity on the real line, decaying amplitudes. This should remind you of Airy equation. I said earlier you can think about Barnabé 2 as a nonlinear Airy equation, and the Airy function, it oscillates out at -infinity, but this is nonlinear version thereof, because in the Airy function asymptotics at -infinity you don't have ln of minus x. That's the first case, bounded oscillatory behavior. Once you move gamma into 1, it changes dramatically, it becomes unbounded algebraic to leading order. This is the Hastings-MacLeod behavior at -infinity. And then lastly, if you exceed gamma equal to 1, then you leave the realm of physical solutions, because the solutions, they start blowing up at finite negative x, and then this translates into some singular asymptotics. These three olive boxes, I didn't mention the people who contributed to all of this. This was quite a long, rich story. It took perhaps 20 years or so until finally all those formulas were pinned down precisely. Here is now the point where this is the only time where I mention actually one of my own results in this area. So these three boxes, they clearly indicate that, gamma equal to 1, there's a phase transition. So, and in particular, the asymptotics at -infinity are not uniform around gamma equal to 1. But actually, you can do better. You can uniformize these asymptotics by using Hilbert boundary value problems and techniques, therefore, by using also Jacobi elliptic functions. I did this myself several years ago, but that's it. Now, second thing is sort of the birth of integrable probability. Solution to Ulam's problem, that is the stuff about longest increasing subsequences. So you start with a shuffle of n objects, you define increasing subsequences, so those are the ones that respect the order of this starting k-tuple, and then you look for the length of the longest increasing subsequence. So here's a concrete example. You look at shuffle of 5 natural numbers, it has a bunch of increasing subsequences. Here are ones of length 2, there's 2 of length 3, but that's it. So the length of the longest increasing subsequence for that shuffle is equal to 3. Alright, but that's all deterministic. So now what you do is you pick your permutation at random, uniformly distributed. And then L of n becomes random variable. So what can you say about its large n asymptotics? Well, many people, Ulam's, I think it was 50s or early 60s, many people then contributed to this area. I only mentioned 3 of them because they gave the final answer. So Beigdijk Johansson, the famous theorem of 1999. You take L of n, you center it, you scale, and then as n tends to infinity, that random variable has a limiting distribution. This is one of the so-called Tracy-Witham distributions, and the same can be written, its distribution function can be written in terms of a solution of Poincare 2 equation. So this U is one of the guys we encountered earlier, this Hastings-MacLeod solution. Now to prove this thing, nowadays, by my count, there are at least 2 books written about this beautiful theorem, and content surrounding it. You need more than just a Hilbert boundary value problem. It's a beautiful combination of various arguments, some of which are written out here. But lastly, you need to analyze orthogonal polynomials. And I showed you earlier that there are Hilbert boundary value problems which allow you to do that. And then what the guys did is they write asymptotics of that Hilbert boundary value problem, and out came formula here on the very. Okay, very good. Last thing, and then I'm almost done. Universality for invariant random matrix models, perhaps the most prominent use of asymptotics for Hilbert boundary value problems. So we had earlier this matrix model, invariant model. I said for simplicity you can think about V of x equal to x squared. But there's more to it. the microscopic scaling limits that come out for your correlation kernel, they are to a large extent independent of the particular choice of potentials, and that is the universality. So it starts by establishing first limits for the Christoffel-Darboux kernel on the diagonal. So that's just the mean eigenvalue density of this object. You can take n equal to capital N for simplicity, and then this thing has a limiting density, rho of v, which is incidentally the equilibrium measure density. So if you come with a nice enough potential, you can ensure that this density is supported on a compact interval on the real line. Right? Let's think about this case. That's more than enough. And now what you want to do is you want to pick different, qualitatively different points on that one interval and study scaling limits, microscopic scaling limits of your correlation kernel. And that has been done. Out comes the bulk universality. This is around points where the limiting density is strictly positive. It's given by the sine kernel, famous sine kernel. This was first established by Leonid Pasteur, by the way, and Maria Shabina in 1997. This was not via Riemann-Hilbert techniques. Blecheritz and Dave and friends, those were Riemann-Hilbert techniques. Now, because it's one interval, there could be points where it goes down to 0. That happens at the endpoints. There, the scaling behavior is different. Out comes a different kernel, which is the area kernel. All right, I will leave it at that. In fact, wrapping it up. So what I did is I walked you first through some historical excursion, making a point at Hilbert's 21st problem. So here's Hilbert on the right and Riemann on the left. That problem should be called the original Riemann-Hilbert problem. Then I walked you through Josip Lemaire's gentleman here at the bottom. His contributions, he came up with an almost solution. You know, to be absolutely honest, he got it wrong. He claimed he had solved it, but no, he didn't. But the techniques that he came up, that he used with, those became very influential later on in applications to integral systems theory. I showed you 5 examples, all of which are underwritten by a particular Hilbert boundary value problem. And then in the last part, I made the case that, you know, although it might seem abstract, these Hilbert boundary value problems are really very useful because they allow you to derive dynamical systems and, in particular, asymptotics for the observables that you're after. Right, that's it. Thank you very much for your attention.
Many thanks. I should start with apologize. I introduced our speaker wrong. It's Thomas Bodner, right?
Oh, that's fine. Don't worry.
Now you're in England. You might be used to having your name wrongly pronounced. Any questions?
So could you turn to page 12 of your slides?
4?
Page 12.
12. Okay.
Yeah. So the equation you wrote down here has a irregular singularity at 0, and the solution has only regular singularity. Is it possible, or are there any other examples so that I can even get rid of this branch point at 0? In this example, the branch point, 0 is still a branch point. Can I cook up, like, is there any example that I don't even have this branch point?
Yeah, so the thing was, what Lemay wanted to do is he wanted to come with, and he did come with transformations that do not change the singularity and do not change the monodromy, right? So I'm not saying you can come here, you could come with a transformation that changes it, sure, but that's not what he wanted to do, right? He wanted to fix that data.
Right, I'm asking a different question. So I'm just asking, like, is there an example that has the equation has this kind of singularity, but the solution doesn't have, like, even have a branch point there?
Yeah, I mean, sure, if you allow some, transformations, I'm sure you can achieve that. Yes, but again, it is not what Lemay set out to do. And if you're interested in solution to Hilbert's problem, you should not be doing that, right? Because you destroy then something that you already know, right? You want to have the monodromy and the singularity there, so you don't want to change that information.
Okay. Okay. And can you turn to page 16?
16, yes.
Yeah. So
Yeah.
yeah. So in this problem, you're there's singularity focus on just like the positive part of this real line.
Yeah.
Is there for this type of problems? Is there an integral formula for the solution?
Yes, absolutely. Yeah. There's an integral equation underlying this which you can solve. Yeah, this is a good point that you make. The Sommerfeld diffraction problem is one of the very few cases where you can explicitly solve the Hilbert boundary value problem with a contour integral formula. Yeah, it's correct.
Is there a good reference that I can find that you would recommend? Like,
well, there are books. I'm sorry, I don't know the titles from the top of my head, but if you write me an email, I will point you to those books.
Thank you.
Yeah, not a problem.
Any further questions?
Could you say a few words about the Hilbert boundary problem associated to the system both have regular or the irregular singular points?
Oh, yeah. So this pertains to this blue box here.
So how to draw the contours and how to give the jump functions, and in that case.
How this comes about, that's what you're asking, yes. So I wrote a review. This is a longer answer, I'm afraid. That's just how it is. I wrote a review paper on nonlinearity about Riemann-Hilbert problems, where I walked the reader precisely through the steps how this blue problem here comes about. And this gives you some idea of why the contours should be chosen in such a way, why the jump matrix. I mean, so okay. Let's accept the contour choice for a moment. So the jump matrix, why it should be look like this is because, of the monodromy definition, right? You want to continue your solution along, say, this loop here, and then the solution should change by what? Well, by matrix G2, right? Because that's the monodromy that you enforce about that singularity. And that gives you an indication why, from one segment to the other one, another one of those G sub J's appears, right? That is because of the monodromy that you enforce in the game. Now, so that should perhaps clarify this particular choice up here. Now, why the singular constraint at the blow-up point, that you have to look at my paper. It is worked out there. So this.
Thank you.
Yeah, sure.
Okay, is there more questions? So, if that's not the case, let's thank the speaker again. Many thanks for the great
Thank you very much.
And I hand to Anton because he's the master here of ceremony.
Okay, so let's have a coffee break, maybe 15 minutes that we have until the start of the exercises and discussion sessions can be extended to 20. Okay, and as I said before, there will be discussions for both of the courses in different rooms. I think here in this room, it will be discussions for the course by Sam Gruszewski, and in A7, one will be discussions for the course for Pavel Etingov, and the idea is that you spend 1 hour in one room and then the next hour in the other. Okay? And figure out how to split 50-50 to go to those rooms on your own as an exercise for exercise session.
Okay. Okay. Thank you. Yeah. Okay, so let's start. So I actually don't know what the discussion session or exercise session what we should do. So here is what we are going to do. Okay, so first I'm Yuancheng Xie. So I'm a teaching assistant for Samuel, like the shortcut problem. And so in the morning we have so our lecturer left us several questions that we were going to take time to solve it one by one. If we have time, enough time, I may also leave some problems to you. And also in the middle, you can in the process, like if you have any questions, you can just interrupt me. And you can also ask any questions like related with this KP theory and the shortcut problem, or other any related question. So our goal is just I don't know. So we have so many people come from different places. I don't know your background. So our main goal is for you familiarize all of you to understand some of these basics. Okay. That sounds okay? Okay. So before we begin, do you have any questions? So in the morning, we talked about like, It depends on you. So for example, like if you the first hour you sit here, you want to take like both exercise sections. So if the first hour you sit here, the second hour you can switch to the other room. Okay. So what is the schedule? What? So we have two classrooms. And we are basically basically like in this classroom we're going to talk about the shortcut problems. The other room we're talk about like teaching systems, and you can arrange your 2 hours. So our first hour and second hour will repeat the same thing. That's my understanding. So you're not going to miss anything. It's just a choice. You want to do this first or that first? Yeah. Thank you for the question. Yeah. Any other questions? Yeah. I need to find someone. Okay. Okay. So if there's any other question, let's begin. So I believe according to my notes, the first exercise looks like something like this. Okay, so if we have L, which is the differential operator, looks like this, I from 0 to n, and ui of x, di to dx to di. Okay, so this is a general differential operator, and we consider its eigenvalue problem, L psi of x equals, so we can denote either E times psi of x or key to the n times psi of x, okay? So the question is the following. Show that it is enough to consider L equals d to the n dx to the n plus I from 0 to n minus 2 and ui of x di over dx to the I. Okay, so here is the question, and I will give you several minutes to think about this. Like why? Okay. No, I mean, if you have an answer, like just feel free to tell me what's the answer strictly. Okay, what kind of coordinate transformation you want?
Just write general transformation. You say x is equal to x prime over x of x prime, and then the vector then d transforms as Jacobian times d.
Oh, you want to transform x equals some other variable?
Yes.
Okay. Something like that, right? And this is the first one. What did you say? The second one? Uh-huh. Lambda some general function psi tilde. Okay. Okay. Mm-hmm. Great. Okay. Yeah. You're completely right. Right. So here's like what I'm going to do. Do you understand what he's saying? First, we actually may not need. Yes. The second one is, might be already okay. Right, because we only need to get rid of the coefficient of u. So un minus 1 of x. Okay. Mm-hmm. 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 Then you want to kill something which is near T1. Mm-hmm. But then if you try to kill it using this delta, mm-hmm. you will obtain something near T2. Okay. And you want to kill in T2. Then you need two transformations. You need two transformations to give you kill M and but if it's a real problem, so only one transformation. You're right. Oh, okay. Sure. So, do you mind that you write it down? What he said? Maybe you know the right. See, we can have fun. Yeah, I mean, if you can show also like a Schrödinger, that's already good enough. I mean, all the other ones it's the same. Yeah.
So now it seems that UN of X is just
Please give microphone to the speaker.
Oh, yeah.
And this function should be, I think, something like that. I hope I'm not wrong. UN minus 1 x dx. Maybe something like this. So when we take n's derivative from it, it's hard to see. Okay, yes. So when we take n's derivative of this product, then we will destroy the n minus 1 derivative. Maybe that's all.
Yeah, can you say that again? Yeah, so, sorry. I think we already, we already got there. So what you want to do is basically something like this. So we will consider a problem like that, right? P to the n per psi, and this L is general. And now we want to consider that we want to consider another differential operator, so it has two properties. First, the initial coefficient is just a 1, and for that we can do it. So first we just divide the leading coefficient because we don't want that to be 0. And if it's not 0, it only has like several poles. We can just divide it safely. So first step we can safely consider this operator. Okay, d to the n, dx to the n, and everything divided by I from 0 to n minus 1, ui of x, un of x, and di to dxi. That's fine, right? Because so this operator xl1, I can still use the per psi as its eigenfunction. So because both sides are only divided up like a function, right? In front. And the second step, I want to get rid of this. So the coefficient like the coefficient of d to the n minus 1 to be 0. And for you to do that, you just consider like a per psi tilde is a lambda x, and the per psi of let's see, x, k, and x naught, something like that. And you just plug this into this differential equation. You want it to be an eigenvalue.
And at last, what you get is L1. Because you take a you're taking derivative like on psi. I'm just dividing the leading coefficient. I didn't affect like any derivative that you take. So it's both sides of this equation. I divided by I divided by I divided both sides by let me see. I divided both sides by un to the x, un of x, right? You're probably right. So let me think about this. So can I just do it? Let me. So I divide other by un. Then what would I have? Okay. So if I do something like this, I will have L just divide by un of x and the psi of x equals the key to the n un of x psi of x k to the. I got something like this, right? Doing the first transformation? Okay. So both of these two methods works. Okay. Okay. Right. So we need to change this also to make. Okay, great. Let's make the. Okay, so let's do this. So psi is f of x, something like that, right? Mm-hmm. Okay. Jacobian times d bar. Jacobian of this transformation. Z. Mm-hmm. Mm-hmm.
We know that the the operator D.
Yeah.
I can write.
Okay. We have like
Maybe I can just. So we have in the single station we have the. I will do this for the most simple station, the lowest order. Lowest order, this operator looks like this. It's u2 d squared plus u1 d plus u0. Yes?
Yeah, I think you didn't open it. Yeah.
I'm worrying about mistakes in my solution. So then there is two transformations. First transformation is x goes to x prime. Then the general thing says that d x goes to x bar. Let's say it will be. And then d will go to the Jacobian d bar. Where Jacobian is now, I think it will be d over x bar, something like this, or d bar over x. It both works. So then you can substitute this here. But also you now can say, that we are solving this problem. L psi is equals, we are acting this on psi, and I do two transformations. First I do this transformation, and then I just say that psi is lambda times phi. Then if you apply this and this, you will have, I calculated, and the answer is lambda j square u2 d square d bar now phi plus
not to use the one. Oh, right. Let's do this. 4 blackboards. So let's do on this 4 blackboards because these are not recorded.
Okay.
Yeah.
So again, you just say that L psi, which is Schrödinger operator, you first do x goes to x bar of x, and the second psi is just some lambda times phi. Then this is written as follows. This is lambda j square u2 d bar square phi plus j u2 g square plus u1 plus d bar lambda d bar phi plus something. I have this written. Plus something. This is function. This is function of lambda. That's right. So now you have 2 equations. First equation is lambda g square u2 equals 1. And this is and let's say that g square is now 1 over lambda over u2, for instance. Then you substitute this here. You substitute this here, and this will give you an equation, just ordinary differential equation for lambda. It can be solved at least locally.
Okay.
This now you solve this for lambda, then you have this is just ordinal differential equation for this transformation. I hope it can be also solved at least locally, so we can both of this equation can be solved. Then this transformation may be introduced. If you just say that the Jacobian is 1, just is just 1, so there is no transformation. This will go to this will have 2 plus 2 d bar lambda is 0. Our equation, and the solution of this equation is just this. For the first power is that this, so it's right. And then for higher powers, this is the same, but equations are one.
Okay.
So you will have as the top power, you will have lambda j power m um d bar m phi, plus you will have some equation d m minus 1 phi plus something. This you can solve. This you can solve. So it's proved.
Okay, thank you.
I think like this.
Thank you. You totally saved me. Okay. Any other questions?
This function will not be eigenvalue function.
Eigenvalue. So yeah. So let's see. So what I think what he said is basically something like this. Okay. So we have some function that from x to some from x plane to c. Actually, we have two kinds of freedoms. One is we do something on the domain. The other is we do something something on the codomain. Okay, we have two freedoms. And one freedom on this side is yeah.
So these are the 2 freedoms you have, right? So you can change variables, or you can change your solutions, and this will kill the top coefficient, right? By just taking, if you take the nth order, if I stand close to you, I'll be. So if you just do this, the nth power of the Jacobian determinant, will kill the top order coefficient, and that's this. So at that point, I get the nth derivative plus junk, starting from the n minus first term. And then if you do this, and I don't know what the right number was, 1 over n plus 1, I don't care. It's a constant, all 1. If you do this, and you just differentiate this product, you're going to get this expression times the nth derivative here, plus you'll get the nth minus first derivative here times that, which will cancel that minus first coefficient. That's it.
So you will still have this. So your eigen function will still comes from here because like we didn't change anything you simply just divide the un and then you will get something like extra psi x over un. We don't have that factor, so we're still fine. Okay, that makes sense. Oh, okay. Convince yourself. Okay, so let me just summarize. So we want to kill two things. The first thing is we want to make the leading coefficient to be 1, and the second thing we want to, the subleading term to be 0. That's the two things that we want to achieve, and we will have two freedoms. One freedom is you see like we have a function that from C to C. Actually, we have two freedoms. One freedom is from their domain. The other freedom is from their codomain. Okay. So you change a variable. That's the freedom that you can always choose on the domain, and on the codomain you can just multiply something, and you use these two freedoms to kill that to fix that normalization. That's basically what you want to do. And I basically showed you wrong way, and he saved me. We're fine with this. At last, if you plug this in, you will get a differential equation, and you just need to know that this differential equation it has a solution. Okay. Because what I asked is, a general differential operator of degree n is equivalent to some other one. I only need to know that some other one exists. I don't need to know its explicit form. That's fine? We're fine with this question? Okay, so we're fine with this, right? Okay, let me see what's the second one. Okay, so the second problem, if we are fine with this one, the second problem looks like this. Okay, so if we have L psi equals p to the n psi, we can already assume that L has their form, the standard form we had. Okay, so L equals d n to dx to the n plus summation I from 0 to n minus 2 u I of x and di to dx to the I. Okay, and then we assume that psi of x k x0 has their following form. So summation s from 0 to infinity, and the cosine of s of x k to the minus x t k x minus x0, and then so the problem is to I think show that you can find cosine of s. So such a solution exists. Okay. Yeah. Right. Basically, there is no conceptual question. It's just like it's just you need to do practice. That's all. So, right. So you have a Leibniz rule, right? So you have Okay, so this is the Leibniz rule you want to use. So do you know how to do you have any idea like how to proceed, or I need to read more things? Yeah, basically what you want to, as I said, what you want to do is you just plug this into there, okay? And this is the nth order differential operator. You use formulas like this, and after that you will just compare the coefficients of k to the negative s for every s, and the left hand side and the right hand side. You must match all of them. And then you will get the differential equations for the coefficients c s of x, and then you solve them one by one. You will find that it's not hard to solve, but you need to do it to convince yourself. Do I need to do more? Or you can help me to do it? Or anyone else? Like, yeah, thank you. Yeah, you can just erase. Yeah.
C0, we can put 1, and also we know that the form of L is the latest follows, but for homogeneity,
Please give microphone to the speaker.
sorry. Okay. Okay, so I from 0 to n, unx di dxi ui. Sorry. So to n ui of x. Actually, we use Leibniz formula. So we have sum j from 0 to I, c g from to I, k. We differentiate this one, so we have k to the power I minus j. Times sum s from 0 to infinity, cs j x k minus s. So, and this is equal to psi s x k minus s. So So this we can actually cancel. And then we need to look at the powers of k. So let's have a look. Let's start from k0. So so for k0 we have we should take here in the sum we should take j equals 0, and here but no, sorry, let me ki minus j, this is in the other direction. Okay, let's rewrite it. Let's resum it. So we have here k to the power I minus j minus s. Yes. So we I'm a bit confused because in this side I see relations with positive powers of k. So there should be equations.
Yeah, so the right hand side you have equals that equals k to the n.
Yeah, sorry, I forgot. Yes, it's equal. Yes. Okay, we have kn minus s. Yes, so we can divide it by here also minus n. So yes, all is okay. So k to the power 0 is really xi0 equals xi0. Okay, but we can do it more in more general form. So we have for the k to the power minus s, we have actually in left hand side we have in the right hand side we have psi s equal to what? So we need to look for the powers for the same. We divided. So we what is better? What is really better to shift? Maybe maybe we just should shift s, yes, and make it so s. So this power it is s plus j minus I plus n. This is actually positive number. So if we take that it goes from g minus I plus n, then here we will have
May I intervene in the interest of time? I'd like to intervene in the interest of time.
Okay.
So we're trying to find a solution of this form, right? So and I'm going to solve for this psi s term by term, right? So I know that psi 0 is just identity. I have a function. So let's look at which step does psi s first appear, or its derivative. So of course, when I compute derivative term by term, I can differentiate here. But if I'm differentiating, I'm just differentiating here.
Yes.
If I differentiate here, this means I'm bringing out a power of k, right? So psi s multiplies k minus s. So the highest order term where it shows up if I differentiated precisely n times here.
Yes.
When I get n copies of k, so I get k to the n. So the highest term in which psi s appears is k to the n minus s. And the coefficient with which psi s appears in k to the n minus s is essentially 1. There are some combinatorics maybe, but I don't care. It appears only once. So this term contributes to k n minus s if and only if I just differentiate it precisely n times here. So this means this gives me an equation for psi s of x in terms of all the other derivatives of all the psi 0, psi 1, psi s minus 1. And that's how I'll compute psi s. So for the term k to the n minus s will be the term from which I'll compute psi s.
But will it be actually equation on psi s, because we have this psi s in left and right hand side, and it can cancel as for.
Yeah. And the highest order term will be a simple differential equation for psi s. The next order term will be some mess. So the psi s will be expressed as the values and derivatives of psi 0, psi 1, psi 2, and psi s minus 1. And then there will be higher and higher derivatives, of course.
Yeah.
But I don't care. So the first time this enters is kn minus s. And then if you just unravel this, you'll be able to compute this from the first time it enters. And then you propagate. Make sense?
Yes.
So do you have maybe some questions of your own? Which is?
Right. Yeah.
Yes. Yes.
Prove this statement. We should the exercise was to prove the statement. My question is how to prove it. You can say just do the same, but you take the general solution of the problem, and then you expand this in the same fashion. You just looked for psi s, but now your psi s your s can be also negative in general expansion of this. In general expansion of this function.
No. I mean, so if the solution will be, I'm looking for solutions of this sort. I never go to negative powers of s. And this starts with 1. So this can be inverted, right? This solution starts with just 1. So it's 1 plus k inverse plus ... So I can invert this in power series and k inverse. And the exponential I'll just invert separately. So that's all.
Yeah, he is asking the next question, which is so the general solution of L per psi equals lambda per psi is per psi. Let me see, per psi tilde equals per psi times ax 0 k. Yeah, I think that's okay. Yeah.
My calculation says that this will true, but I think it's a mistake. we should, how to solve it? We should take the general solution and expand it just as the powers of the k. As the powers of the k with coefficients which are atoms. Maybe I can. So what should this be? How do we determine what this is, right? That would be one question. Yes. So this general solution, what I have here, psi twiddle,
Okay, so if I have any general solution psi twiddle, how does it differ from the psi computed here, right? So I should be able to tell this just by looking at the expansion of psi twiddle at x naught. So I'll do that. That will define my A, right? Because I know secretly what A should be. If this is true, just evaluate both sides at x naught. This will, of course, I mean, suppose this is true. I know exactly how this evaluates at x naught. The series is just 1 at x naught. So this is at x naught, this is just 1. Wait. So at x naught, plug in x naught here. Plug in x naught here, you get 1. Plug in x naught here, you get stuff. So this better be the value of psi twiddle at x naught. Now you know what to check. And it will work.
Right.
More questions? So for questions about Jacobians, I'll continue with Jacobians tomorrow. If you have never seen Jacobians, look around the room, find somebody who has experience with Jacobians, grab them and learn from them for half an hour tonight. That's your best solution. I'm also happy to answer questions, but I'm alone. Other things we should do with differential equations.
So it's quite complicated. It's not so. And the question, I guess, it would be nice to discuss this.
So are you asking why Q is a polynomial, basically? Okay, so what's the setup? So the setup is I have L1 and L2, and I know they commute, right? For each E, I have the space LE, which is a space of functions psi, such that L1 psi is equal to E.
Yeah, they couldn't see on this blackboard. They couldn't see these two blackboards. It's only like they.
So we can look at L, which is a set of E eigenfunctions, right? For a fixed E. E is fixed. So this is n-dimensional, just because I can choose different answers.
Yes, it's clear.
Okay. So then I have QE of alpha is a characteristic polynomial of L2 restricted to the space L of E.
Yes,
right?
it's also clear.
Okay.
And it's a product of eigenvalues, difference of eigenvalues. So alpha minus lambda from E. Yes.
Okay.
And yes.
Okay. So I can do that. And then what you're asking is, how do I know that the AIs are algebraic functions of E, basically? So I mean, you should do the details, but you can do a different approach. You can consider L prime of E, or maybe let's call this L1. And let's do the same, but L2. And let's call it L2 of alpha, just to confuse you. Okay? So this is a space of solutions of this equation, right?
Yes.
And then I'll get ... I'll get, this was Q. This, now I'll get Q alpha of E.
Yes,
right?
exactly.
And then I can check that this is equal to QE of alpha, because this is the same condition. This is just the condition that I have a common eigenvalue. So it
Yes,
must be
exactly.
the same. But this guy is manifestly a polynomial of E. This guy is manifestly a polynomial of alpha. So the
Yes,
whole thing is a
that's
polynomial of
nice
both.
proof. Okay.
Make sense?
Yes.
And you should also compute this carefully, because I was sloppy. There are n's roots and m's roots, which I
Yes,
ignored,
it's
but-
the details, but the core is now clear.
So it's finite generation. And you can
Did you hear me say the words projective model in my talk? I'm allowed to not answer. Okay. Thank you. Uniqueness being what? The thing that there exists a unique solution? Well, because you can just solve uniquely.
He asked like the third one, L psi tilde equals lambda psi tilde.
Yes. So this is not uniqueness. This is to say, if you have this, then
other
they
freedom
must differ by that.
you can
right?
have.
So this A is just the value of psi. So yes, yeah. So this will be uniqueness. So the proof. I mean, I never said the proof, so I cannot repeat it, but I can tell you how it goes. So I know what A is, right? So if you want to prove uniqueness, this is 1. But then I told you before, we know why uniqueness works because we can just solve term by term uniquely. Because each psi s is expressed as all the derivatives of the lower ones. That's all. And the same argument works to prove this more generally, right?
So if you have your leading term, like when we deal with psi, like leading term is 1, and then it's unique. Now you know that for psi tilde, the leading term is a of x0 to k, and then you can just plug in, use the same method to show that it's unique.
I understand, but it's hard for me to ask this question in English. I will ask. So you just said that we can do it point by point. And psi x0 we can do this point by point. So somehow there is something to check, right? I'm not claiming this is completely trivial. I somehow had to convince you that this works precisely. So what we're doing is we're doing some normalization problem. We're saying I have a space of solutions, which is of course infinite and big, and I don't know how to deal with it. But I'd like to know how to pick an element uniquely. And the statement is that you just do this normalization. It requires the first coefficient to be just 1, and then you require everything, the whole thing to vanish. Otherwise, I mean, all the other terms to vanish at x0. And that turns out to be unique. The proof of this is you just construct the solution term by term, and you are solving uniquely an equation, so no problem. But then for that, you just check the same. The proof works the same way. It's something to check. There is no general machinery that tells you this must be the case. It's not clear. Okay? What's the what?
Formal solution, you have a formal power series. You don't care about whether it's convergence or not. You plug it into the equation. If it satisfies the equation formally, that's a formal solution. So formal means you don't care about the convergence. We did not do anything about convergence, right?
So a formal solution for me just means a solution of this form, which is just a formal series, right? This is a formal power series in K inverse times an exponential, which is here for good measure. This depends on x0, yes.
Yeah, x0 is the reference point you choose.
This part does not depend on x0. There is no x0 here, right? So a formal solution is a solution of this form times some exponential. That's all. And I'm not worried about the convergence of the series. It may not converge, and I'm not at all trying to do anything here.
Yeah. Yes.
Everything today has been formal solutions. No geometric solutions, no convergence, nothing. Just a formal solution is a solution which has this form for some x0. But then, of course, you can easily check that if it has this form for some x0, you can just multiply by a constant, which is e to the k x0 minus x0 prime. It will have the same form for all x0. Doesn't play a role. It's just a convenient normalization.
Any other questions? Okay. So we have our fourth problem, something like this. Okay. The first one is find out like we have an operator of L1, L2, they commute, and degree. So order. Let's see. Order of L1 is 2, order of L2 is 3. Find out like when this happens. You have two differential operators when they commute. And this is the simplest example that we do. You write down a general differential operator of order 2 that we already normalized, a general operator of order 3 that we also normalized, and find out when they commute. It may take time to do calculation, but at least you need to know, like, write down something to the step that you know what to do. Yeah. Mm-hmm.
I think in a few minutes you should all go and learn more about Hitchin systems. But before you do that, let me point out one thing here. That I was cheating in the talk purposefully. So we can bring L1 to the standard form that we discussed at the beginning. Or I could bring L2 to a standard form. Okay? It's not at all clear that I can bring both of them to the same standard form. If I just have two arbitrary operators that don't necessarily commute, that I know nothing about, I cannot bring them both to a standard form. So your first exercise would be you choose L1 or L2 to the standard form, convince yourself that if L1 and L2 commute, then the other one can also be in the standard form. Once you're done with that, then you should really be computing the commutator, right? So there is a missing step. Otherwise, you have an arbitrary second order differential operator and the third one in a standard form. But of course, if you just look at the top degree, I mean, the fact that the top coefficient is 1 is obvious because you differentiate and the derivative of that thing better be 1. So it's a constant, right?
Mm-hmm.
So of course you can rescale by constants, plays no role. But this is something you should check. It doesn't come quite for free. And you should go and learn about Hitchin systems.
Okay.
I'm happy to answer questions privately.
Okay, so if you have further questions, you can just ask us privately, like after class or any other time. Okay, thank you. What?
see how it goes second time around.
Okay.
There are no restrictions to no singularities. If I just give you a pair of differential operators, they satisfy some polynomial relation, and there is no control on what singularities the resulting curve will have.
So you mean if we there's some point in the singularity we can construct the operator, or
if I what?
If we fix some point we claim this is the singularity we can.
No, I don't mean by claim. I guess this polynomial in C2 it has some singularities, so it doesn't. We don't get to change that. I mean, I'm not yet solving the inverse problem. I'm not saying that if I have a curve in C2, I can construct something different. But all I'm saying is I have a very differential.
没有写那个艾丁高夫的练习。
怎么了？哦，对。
What's the idea of the last exercise on the brothers? Compare A and B. The next exercise.
Yeah. Yes. We did not get to yes.
It was the hardest for me.
Okay.
I don't really understand. Maybe I read down something wrong.
So what did you do? I think that's let me see. I think that's the same as mine. Mine, right? So you have to compare this with that.
I don't understand what is this.
So because you have some kind of eigenfunction and you normalize. So you just look at the normalizing condition. And then in the previous one, we said that any eigenvalue functions looks like something like this.
Yes. I don't. Yeah. Here, where isn't the exponent? It's is the same function c multiplied by exponent, and here it's multiplied by.
Right.
B is equal to exponent or what? This moment I didn't understand.
Let me see.
Or it's another something to do. I don't understand the definition of B.
Let me see. Okay, we want to show this equals that, right?
Yes. And but why did we solve this C multiple exponent? Where this one appears?
Why this one appears?
Yes, where this one appears?
So I think we just we have this one. So this is just a you multiply it.
Yes.
You multiply it and then you so this and that you will cancel one term and it becomes kx minus x0 prime, something like this. Okay. But this is not that because you still need so you still need it to be what? Let me see. This to satisfy the. This to satisfy the differential equation. Why this doesn't? This
because it is not the eigenfunctions.
It's not eigenfunctions?
Yes, it was said. I just remember from lectures. The lecturer said that this is not the eigenfunctions, so it's not equal to this. But maybe
it's not the eigenfunctions.
It's not. Okay, I'm not sure.
Yeah, let me think about it.
Maybe we should from this time.
So this by definition, this is what this is. It's the eigenfunction normalized at x not equals x not equals identity, right? And we need so this is not because you see when we normalize this, we want Xc1 x0 other Xc s x0 equals 0, but we don't know Xc I x not prime equals 0 because our normalization actually asks. Our normalization actually asks like other than the leading term, all the other terms because it vanishes. So, can you turn to your let me see the definition. The definition of this guy is like you have your leading term equals 1. I think I made a mistake. Yeah, here is 1, and all the other ones is 0. Okay, but it's not this one because we know that the leading term is 1, but it doesn't like Xc I x 0 prime is not 0. We cannot make sure that.
Why it's not 0?
Because Xc yeah, but Xc I x, how we solve them? We solve them like Xc I x 0 is 0, not x 0 prime. Because this one we normalize when at x 0. So this is like psi x k x naught. Okay.
And this is
that means other coefficients when you take Xc I x naught it is 0, but not necessarily x naught prime.
Yes. And
so this is not the normalized like eigenfunction yet.
Yes. And what you want to do next?
Right. Let me see.
Maybe someone here or here must be.
Let me see. Then
not x0, but different x0. No.
Different 0.
I'm sure maybe here is something like that. Not it can be.
Yeah, I don't know what this part what he wrote. Let me think about this. And I would get back to you later. 没有啊。我看 Thank you 啊？是吗？他讲的什么计算？我想听。啊？好吧。X 那个刚才那边过去多少人？有多少人过来？啊？就是刚才那边没几个人吗？我知道，但是他们结束了应该过来。
因为那边已经开始新的一轮，我才过来。
好吧。
你们有定时6点开始吗？
没有定时什么时间？本身是5点半，但是第一个已经晚了。OK。行。
或者你再等一会儿。
反正。
刚才还陷入到第一个问题的里面。
谁个？
Okay, so so let's begin to do. So this is the exercise session for the shortcut problem. And my name is Yuan Chengxi. I'm your TA on this course. Okay. So so the goal of this exercise course is like we want to understand like other problems that we didn't fully understand in class, and then we deal with it like in the recitation one. Okay. So we will either just finish the problems left in their class, or if you have any questions, you can just interrupt me in the middle, and then we can discuss about it. The goal is like we try to understand as much as we want. Okay. So before we begin, do you have any questions? Like from their morning session? We're fine. You don't have any questions? Okay. Oh, okay. Then we can do some exercise to try to see what we have learned. So let's see. We have a first question is something like this. Okay. So we consider the differential operator, a general differential operator like this. And their question is, show it's enough to consider. So L equals d to the n dx to the n plus, okay, I from 0 to n minus 2 ui of x di dxi. Okay. So you see, we have a general differential operator. We want to understand its eigenvalue problems. Like this is a differential operator of degree n. So we can set that. So L per c equals k to the n times c. Okay, that's an eigenvalue problem. That's what we want to understand. Okay. And the question asks like show that to understand that problem is equivalent to understand like the following one, which looks like simpler. Okay. I will give you like several minutes to think about it. That's what I did, and and you will find that you have to find the eigenfunctions, but then it's just a try. You can just try it. Okay. Try it. Write it down, and then we will see whether it's okay or not. Okay, I'll give you like 2 to 3 minutes to write it down and tell me what is okay, what is not okay. Okay. So as you observed, actually there are two things we need to do, right? So compare the first operator and the second one. First, we need to make their leading coefficient to be 1. The second, we need to make their coefficient u n minus 1 goes away to be 0. How we achieve that simultaneously? That's our goal, right? Okay. Yeah, the problem is clear, right? So we. That's exactly the question is asking. What kind of transformations that you should do, or you can do? And if you find out other transformations that you can do, then you will find out like why you can normalize a differential operator like this. Let's just think about it. So first we have we want to find a differential operator like that's so we for example we have a function, right? It's from C to C, and we do transformations on this function. What kind of a transformation we're allowed to do? There are only two types of transformation. One transformation is on the domain. The other one is on the codomain. Okay? That's a hint. So anyone want to try? Okay, let's try this. So let me make this hint a little more explicit. So first, the transformation on the domain, you can always do something like this. Okay, right? So that's a transformation in the domain. You change variables, and this f can be arbitrary. You make it to be a function in a differential operator in a z plane. And the second transformation that you can do is you see we have a psi, and then you can also, times anything like this x and k and psi. You multiply like a function. Okay. There's two kind of transformations you can do. And more completely, you can do like a composition, but for this question, like this should be enough. What?
Should f be automorphism
Of C. Yeah, I mean any reasonable function. So, but the point is like, what's the function of f? Why you want to do this kind of change of variable? I said that there are so the hint is already quite clear, right? We need to do two things. First, to normalize the leading coefficient to be 1. Second, to make un minus 1 to be 0, right? That's the two things what we want to achieve. And now we have two kinds of transformations that's allowed.
So we consider arbitrary functions for polynomials. We have to say what is f and what is lambda.
Yeah, you have to tell me like what is f, what is lambda. Oh, okay, so let's make a simpler example. So let's see, what if we have a ux and a partial x squared minus plus u1 of x and a partial x plus u0 of x, right? So the first thing you want to do is just to kill this one, okay? And then we can just do a change of a variable that from x to partial z. Oh, well, sorry, it's not. So this whole thing, act on psi, we have a Kn2 psi, okay? And first we want to normalize the leading coefficient to be 1. That's, you need to do one kind of a transformation, and after that you do another type of transformation, okay? I will give you 2 more minutes to make this happen. Let's just try to, if there are, if it's too complicated to consider like a general one, we can just restrict it to second order. That's also fine, because the general one is just more general. The idea is the same. Okay. Okay, so do I have a volunteer to finish this? This.
I suppose that we should find such f that when we write dz square and transformate it through the variable x, we have leading term like that. Huh? Yeah. So we know that so we need that don't equal, but have the same leading term with this. I don't know how to write it. Well, this is equal to and this have leading term plus something times dz. Am I right or not? So we should find such f that this equals to 1. Excuse me? So am I right? Or so what we should do, we should find such f that this equation holds.
Yeah, let's just assume this f exists. Okay.
Okay. So this is the right way to do this, or?
Yeah. And now you have to kill un minus 1.
Okay.
You don't want to continue?
I can. Okay. No problem.
What? Yeah, formally it always exists. So formally you solve f like just you find f just by solving some equations. That will depend on what's your U2. Because you give me different U2, then my f will depend on your choice of U2. Mm. Mm-hmm. Right. Right. We just need one condition for f, right? We just need the leading coefficient to be 1. So then we need to find we need to solve a differential equation, right? Maybe a nonlinear one. So there's a whole thing to be 1. That's all. Like that's a differential equation for f of z. F of z. That's fine. Okay.
So we do not specify what kind of function we consider. Well, I think for functions which are okay, let's move on.
So our next goal is to use another transformation to eliminate un minus 1. Okay.
Well.
Let's write on the this or the other one.
Okay. What does it mean? We have.
So we at this step we can already assume that the leading coefficient to be 1.
Mm-hmm. Okay, so we want to Am I right that we should find something like this? So
So what we do? So you see now we can already assume that L equals because we did the first step, we can already assume that our L looks like something like this, right? That's after the first step, and then you plug in. You just you apply this to the other functions. So let's see. You apply this to lambda psi. and this you ask it to depend on x, and the k x naught, and then after you apply that, you know that so you will have so let's see, partial x square. This whole thing applied to we just need to find it's this term, and then you can use the Leibniz rule, like this is the following thing: partial to the k, you apply to f, and then what's it? It's I from 0 to k, and then k choose I, and then you have f, take i's derivative, and then k minus i's derivative, right? And then you apply this to that, and then you will find like what's your so then this will give you like lambda prime of x and a partial. This is a contribution from the first term, right? Right, because there I only need to find what's the coefficient of the partial, and this will give me a coefficient of a partial because so I always get like if k is bigger than 1. And the next one is just a u1 of x partial. And I want the coefficient of this to be 0. And this to be 0. So what do I choose? I just choose a lambda to be a solution for this equation. And that's all, right?
Right, but it is like in another direction.
Right.
Okay,
but,
yeah.
Yeah, but the idea is something like this, okay?
So we should take inverse of this function.
Probably, yes.
Okay.
Okay, thank you. So we're fine with this? Okay, thank you. So we're fine with this. Any other questions? Now let's, if we don't have any other questions, let's do the second exercise. The second exercise says something like this, okay? So since we already have our normalized form of L, and then, so we have L psi equals k to the n psi, and psi equals, so this is the formal series solution. S from 0 to infinity, and Cs of x, k to the minus s, and the exponential k, x minus x naught. So we want to show that there exists a unique such kind of a solution, and actually we already did something in class, so we know this, okay. So if we apply this differential operator on one of these terms, like Cs of x, k of k to the minus x, e to the k x minus x naught. Okay, so there because we are taking derivative with respect to x, and this term doesn't depend on x. So we take derivative either on this or on that. Okay, and when we take derivative on this, we just bring down like the power of k, and on that we just take derivative. Okay, so this will give us something like this: k to the negative s, and then we have d to the I, d to the x to the I Cs, and plus d I minus 1 Cs, dx I minus 1, and then k, and plus dot dot, and exponential k, x minus x naught. Okay. Now we want to, so the question is, solve for next. So 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 solve for next. Cauchy S. So how do you find like Cauchy S? Like their coefficients like recursively. Just to make sure that you know how to do it. Okay, so the question is just convince yourself that there's a unique formal power series solution. So what's the meaning of a formal? That means like we want a solution like this, and we don't care about whether it converges or not. You plug it into the differential equation, and in some sense it satisfies the differential equation. Then it's a formal power series solution. Okay. I'll give you 2 to 3 minutes to think about this, and then. What? Actually, it's from you don't need to. It's from the first. So you take your two there's the whole one. Their first two are why the bracket is from their brackets above. So what you need to do is convince yourself why you can do it like you can find every Cauchy S.
So, what's your quest? What's your problem? So you are given the Cauchy S, try to find the Cauchy S plus 1.
Something like that. But so you notice that actually first I require that we have some normalizing condition. We require that Cauchy 0 of x we require it to be 1. Okay. So we normalize that this solution here has to be 1. The leading coefficient we normalize it to be 1. And then you need to convince yourself that after I fix this, you can find a unique solution. At x not, right. Sorry. Yeah, at x not.
For the Cauchy S.
Hmm?
The value of Cauchy S at x not.
Right. I need to maybe something like this. S from 0, infinity, x, s, right? Okay.
You need this, right? You have greater than 0.
Mm-hmm.
And you need to sign not x.
X not. Or any point?
This needs to be just 1. This needs to be identity.
Okay.
So you want this to start with s is 0. This one is not there.
Mm-hmm.
So you just want your psi to be e to the k times x minus x naught times 1 plus psi 1. And this power series evaluated at x naught needs to be just 1. That's what this is.
Mm-hmm. Okay. Thank you.
When you write psi in this form, what does mean equality of L psi to
That's an initial condition. So you have a.
Whether this makes sense for series of this form. Yeah. So do not expand this in power series. I'm aware that if you try to expand this in power series, this has positive powers of k, which are ugly, right? Then don't do this. This is a formal power series in k inverse. No problem with that. That's a black box that somehow has this written in it, means not. I know how to differentiate these things term by term. If I differentiate term by term, this will always stay, right? I cannot get any explanation. So you just formally differentiate this term by term. You'll get another expression of the same sort. You formally include them term by term.
So it's equation of formal power series.
It's not a formal
Yes.
power series.
Formal
power series in K inverse times exponential.
Right. You forget about the exponential.
I, right? I differentiate I times, the most I can get is this, right? So I get k to the I times is, right? So if you look at this derivative, the highest order term picks up an extra i's power of k, right? So you can see where the derivatives of this term will enter. They will enter in I plus 1 terms in the expansion. That's the highest one. Just solve and look where k to the power I minus s appears, right? It appears here for the first time, right? So this influences the highest order term that psi s is going to influence is going to be k to the power n minus s, right? So solve for that from that term, and then proceed. That's what this says. Writing this on the blackboard is as messy as writing this on a piece of paper, but that's how it works.
So we need to see more, or it's already enough to convince you that that you can find the QCS like recursively. So basically, what you do is you just plug this into the differential equation, and then their power term means you have like their exponential on both sides. That actually goes away, right? And if you just take away that, and then on both sides you have just a negative powers of a k. And then you compare the coefficients of other powers of a key, then you can find QC of S like term by term, uniquely. So what you should convince yourself is like this C of S that you can find it like uniquely. If I already said specified like the initial condition at x equals x naught.
Uniquely when we say that the zeros delta is equal to 1.
Mm-hmm.
I think I know what you're confused about. So it looks to you like I didn't really need this condition properly, right? But look at the highest order term. There is no differentiation. So I'll get just, if it's n or the derivative that I'm taking, I'm just getting k to the n. But that's going to cancel on both sides. So I need to look at the next order term. And the next order term will involve the first order derivative of psi. So I'll know the first order derivative of psi if I'm doing this honestly. And of course, if I know the first order derivative of psi s, I know it up to a constant as a function of x. This is what fixes the constant, right? So this term will automatically cancel the way my equation is set up. So if I take the nth derivative here, my highest order term is this, right? And then for the next order terms, there'll be an equation which will involve the first derivative. Okay. So that's why I need this. And of course I need this. That's clear. Correct. Which is why writing this is a bit long and unpleasant.
Right. Because we already solved that. Basically, in principle we solved our first exercise, right? So we can assume that our differential operator is in their normal form. Yes. What? Where did we use this? In principle, you don't need to use this, but that can simplify your calculation. So do I need to see more?
You should just write down the first of the three terms. Write down and take n to be equal to 2. Maybe 3. And write down the terms, up to order 3 minus 2.
Yeah, and also like if you don't like answer other differential operator differential equations, just consider like other two. Yeah. Okay. So do you have any other questions like on this problem? We're fine with this. Okay. Let's see what's our next one. Okay. So our next problem looks like this. We showed that okay, if we specify this this initial conditions, then we have a unique formal power series solution like that. Then so there are third exercises. So if so any formal power series solutions, formal solutions of L psi equals e to the n psi as their form psi xk equals so psi x a we normalize x naught ax akx naught. Okay. You have a question? Formal solution I just said. So we look for solutions like that. Psi x like that. So we have our power series part that deals with actually that help us to get rid of the the positive powers of k, and then all the rest is a power series that we put in a series that has other negative powers of k. We don't care about whether it's a convergence or not. We plug it into the differential equation, but then it satisfies the differential equation in a formal sense. Yes. This one. Okay. Yeah. So what kind of freedom you can have? Okay, we already know that if we specify like the initial condition at x naught, right? Any solution looks like that. You plug into the equation and it satisfies the differential equation. Oh, this problem is asked you. So the second one we deal with there's following situation. Okay, if we specify the initial condition at some point x equals x naught, so we make x. So we put the condition that x c 0 x naught equals 1, and c I of x naught equals 0 for other I bigger than 0. Okay, if we put that condition, then we can have a unique formal power series solution, right? Formal solution. now if we don't put that condition, so then what's the other?
So what condition are we following?
This condition. So we want to find basically other formal solutions of this differential equation. And what you need to show is that like all of them looks like that.
So what about the function a k x 0?
Any
arbitrary function.
Yeah. So basically you see like formally let's see. So basically you see like the eigenvalue problem is with respect to x. Okay. And if you multiply any function that is independent of x, it's an eigenfunction of the original differential operator, right? There is no problem with that. So one direction is like any functions of this like have the form like this is actually a formal eigenvalue eigenfunction of the differential operator L. That's fine, right? So you need to basically you need to go to the go through the other direction. So if I have a formal eigenfunction, I need to prove that it looks like this. I mean, as long as it doesn't depend on x, right? I multiply any function of k and x0, like
this is relative quality of formal power series in k inverse.
Yeah.
But do we consider A of k?
It can be also a formal power series of k inverse, right? or it can even contain k, the positive power of k.
So we do not ignore it like exponential.
No.
Since the original equation is an eigenvalue problem.
Right.
So it is linear. So the solution, the last solution is automatically a solution.
Yeah.
Yeah, because it is
it's automatic. Right. It's automatically one solution. But so the question we are asking is like you need to show that other solution looks like this. So that's one of the direction. Right.
But by linearity, two solutions, the sum of two solutions is also the
Yeah. Yes.
So you guys have to go eat, so do we all. So I'll interrupt here. But so, I mean, what this really is trying to say is that there is a unique, this in some sense, the spectrum is simple. I don't want to make this precise. But this says that for any k, there is a unique solution up to scalar, right? If you are worried that, of course, I'm writing k both here and here. And so I'm perceiving this as a function of x and k. And what the statement is that if this has this form, then of course I can write A as a quotient of this and that. And this I can invert. The exponentials will happily cancel out. I will not have to worry about that. Here, this is a power series in K inverse, which start with identity. So they're an invertible power series. I can invert them in power series of K inverse. So this means this divided by that will also be a power series in K inverse, which is what this will be, a formal power series in K inverse. So this is a formal power in K inverse, and we will not discuss how it depends on x naught, right? What is that thing? That's easy to evaluate. Just plug in x equal to x naught. If you plug in x equal to x naught, this is just 1. I mean, it's exponent. It's really 1, right? There is nothing there. So it's not there. So this is just the value of that at x naught. So I know exactly what to take. So your exercise becomes define A to be psi of x naught k. Prove that this is true. Proof, step by step on the power series. which I'm not going to do, and you need to have dinner. Yes. So basically, you divide this by its value at x naught, right? Then this is still a solution, which will satisfy the normalization. So it's unique. So if you believe that this was unique, you should believe this. This is sort of to say that there is a unique solution. I cannot say unique solution with eigenvalue k. K is not an eigenvalue. Eigenvalue is k to the n. So this sort of says the space of solutions is n-dimensional, except I have a lot of trouble saying this because there are different k's here, there's different power series with different exponentials. We are supposed to leave. I am happy to talk over here. We can start going to dinner and not. Some clear sciences.